Look up at a clear night sky, away from the city lights, and find that deepest, darkest patch of emptiness between the stars. It feels like a void, a perfect nothingness. But what if that emptiness isn't empty at all? What if it's a place where the universe itself breaks, where the rules of reality as we know them simply cease to apply? That is the true nature of a black hole. Not a hole, but a cosmic point of no return, a gravitational monster so powerful that not even light can escape its grasp. And at the very center of that infinite darkness, hidden from our eyes and our instruments, lies the greatest mystery of all, the singularity, a point of infinite density, a place where space and time themselves are crushed out of existence. We have a name for it, but we have no idea what it actually is. For decades, these cosmic giants were just theoretical phantoms, the bizarre predictions of Einstein's equations that many scientists thought could never actually exist in nature. Then we began to find evidence: pulsars orbiting invisible companions, stars whipped around by something unseen, and finally, in 2019, humanity witnessed the impossible, the first ever direct image of a black hole's event horizon, a fiery ring of light circling the abyss at the heart of the galaxy Messier 87. That image, a shimmering orange donut of superheated gas, was not the end of a mystery, but the beginning of a deeper one. It confirmed their existence, yes, but it also shouted a profound question into the void. What truly lies at the heart of that darkness? What happens to matter and energy once they cross that ultimate threshold? That question is the gateway to a journey we are about to embark on together. Despite everything we think we know, black holes and their enigmatic singularities remain the universe's most profound and stubborn enigmas. They are the places where our two greatest theories, the cosmic scale rules of general relativity and the subatomic weirdness of quantum mechanics, meet and spectacularly fail. They are the ultimate paradoxes, objects that seem to both create and destroy information, that might be gateways to other universes or the final endpoints of existence. In this video, we will voyage through 30 of their most perplexing unsolved mysteries, from the fiery paradoxes of their birth to the chilling implications of their eventual death, from the warped spacetime around them to the terrifying unknown within. This is not just a list of facts. It is an exploration of the very edge of human understanding, a guided tour to the frontiers of physics where the answers we seek are as dark and alluring as the black holes themselves. So, let's begin our descent into the unknown. Our first mystery strikes at the very heart of physics, a puzzle so profound that it caused Stephen Hawking himself to make a famous bet he would later lose. It's called the information paradox, and to understand it, we first need to grapple with one of the most sacred principles in science. Information cannot be destroyed. Think of it this way. If you were to burn a book, the pages turn to ash and smoke. It seems like the story is gone forever. But in theory, if you could collect every single atom of ash, every molecule of smoke, and track the precise energy and light released, you could, with impossible precision, reverse the process and reconstruct the book perfectly. Every letter, every word would be there. The information about the book's state was never truly destroyed. It was just scrambled into an incredibly chaotic form. Quantum mechanics insists this is a fundamental law of the universe. Information is always preserved. Now, bring a black hole into the picture. Let's throw that same book past the event horizon. According to Einstein's general relativity, the book is gone. It's crushed into the singularity, leaving behind only 3 detectable properties for the black hole: its mass, its electric charge, and its spin. The rich, detailed information about the book, the specific arrangement of atoms that made its paper, its ink, the very words it contained, seems to have vanished from our universe entirely. For decades, this wasn't seen as a problem. The black hole was a permanent vault. The information was still somewhere, just permanently locked away. Then, Stephen Hawking revolutionized our understanding by discovering that black holes aren't actually black. They glow. Through bizarre quantum effects happening right at the edge of the event horizon, black holes slowly emit a faint mist of particles, what we now call Hawking radiation. This process causes the black hole to lose mass, to evaporate. Over trillions upon trillions of years, a black hole will eventually shrink and, in a final pop, vanish completely. And here lies the paradox. If the black hole evaporates into a featureless cloud of Hawking radiation which, according to Hawking's original math, contains no information about what fell in, then the information about our book is irretrievably lost. The universe's ultimate vault has not only been emptied but has disintegrated, violating the core rule of quantum mechanics. Physics is left with a fundamental contradiction between the smooth spacetime of general relativity and the information-preserving requirement of quantum theory. So, where does the information go? This is where the mystery deepens, and theoretical physicists have proposed some truly mind-bending solutions. One leading idea suggests that the information never actually makes it inside. Instead, it's somehow encoded or painted onto the two-dimensional surface of the event horizon itself, a concept known as the holographic principle. The three-dimensional information of the book is stored on a two-dimensional boundary, and then slowly and chaotically radiated back out as the black hole evaporates. It would be like scanning every page of that book onto the surface of a balloon, and then as the balloon deflates, the information is released back into the world, albeit in an incredibly scrambled form. Another, even more radical proposal is the idea of a firewall. This theory suggests that instead of a smooth event horizon, there is a literal wall of blazing high-energy particles that instantly incinerates anything that tries to cross. The information is destroyed right at the door, but this solution is deeply unsettling as it violates Einstein's principle that an astronaut falling into a black hole should not notice anything special as they cross the horizon. The debate rages on, with each potential solution solving one part of the puzzle while creating new, equally strange problems elsewhere. The information paradox remains a glaring signal that our understanding of reality is, at its most fundamental level, still incomplete. While the information paradox confronts us at the event horizon, our next mystery pulls us inward, toward the ultimate heart of darkness itself. What exactly is the singularity? This is not just a question of what it's made of, but a challenge to our very understanding of reality. According to the pristine equations of Einstein's general relativity, when a massive star collapses under its own weight, its matter is crushed into an infinitely small point. Not just incredibly small, but a true mathematical zero, a point with no volume whatsoever. This point contains all the mass of the original star, leading to a concept that is almost impossible to wrap our minds around: infinite density. Gravity at this point becomes infinite, and the fabric of spacetime curves to a degree that is literally off the charts. At the singularity, the equations of general relativity produce nonsense answers. They break down completely. Space and time, as we define them, simply cease to exist. This prediction of an infinite point is where our two greatest theories of physics enter into a direct and violent conflict. General relativity, which masterfully describes the universe on the largest scales, the dance of galaxies, the bending of light, the evolution of the cosmos, seems to demand that singularities form. Yet quantum mechanics, the wildly successful rules governing the subatomic world, utterly rejects the idea of infinities. In the quantum realm, everything is grainy. Energy, momentum, and even space itself are thought to be quantized, meaning they come in discrete, tiny packets. The concept of a perfectly smooth, continuous point of infinite density is an anathema to quantum theory. It would be like saying a digital image has infinite resolution. The quantum world insists there is a fundamental pixel size to reality, a smallest possible unit. So, we are left with a profound standoff. One pillar of modern physics predicts a singularity must exist, while another pillar declares that such a thing cannot possibly be real. This contradiction is the clearest signal we have that our current picture of the universe is incomplete. Physicists are convinced that a deeper theory is needed to resolve this conflict, one that successfully merges general relativity with quantum mechanics. This holy grail of physics is known as quantum gravity. We already have a quantum theory for 3 of the 4 fundamental forces in nature: the electromagnetic force, the strong nuclear force, and the weak nuclear force. But gravity, described so beautifully by Einstein's geometry of spacetime, has stubbornly resisted being quantized. A working theory of quantum gravity would, we hope, tell us what truly resides at the center of a black hole. It would show us that the singularity is not actually a point of infinite density, but something else entirely. Several fascinating possibilities emerge from this search. One leading idea, known as loop quantum gravity, suggests that spacetime itself is woven from a fabric of tiny, finite loops. Under this theory, the immense gravity of a collapsing star would not be able to crush matter to an infinite point. Instead, it would meet a powerful repulsive force generated by the quantum nature of space, causing the collapsing matter to bounce back. This could mean that what we call a singularity is actually a gateway, a portal to another region of spacetime, or perhaps even an entire new universe. Another concept, string theory, proposes that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. In this framework, the chaotic conditions at a black hole's center might be described by a dense, fuzzy ball of these strings, often called a fuzzball, which would have a finite size and avoid the infinities of a classical singularity. The true nature of the singularity, therefore, is not just a mystery about black holes, but a mystery about the fundamental laws of the cosmos. Unlocking it would require a revolution in physics as profound as the ones brought by Einstein and Bohr. It would mean peering into a realm where space and time are born from something more primitive, and where the universe itself might reveal its ultimate building blocks. Until we have that unified theory, the singularity remains the ultimate symbol of our ignorance, a mathematical warning sign placed at the edge of known physics, pointing toward a deeper truth we have yet to discover. This clash between quantum mechanics and general relativity leads us directly to our third mystery, a concept so radical it seems ripped from the pages of science fiction: the firewall paradox. If the idea of information being permanently lost makes physicists uncomfortable, the proposed solution of a firewall makes the situation even more bizarre. Imagine our brave astronaut, having survived the tidal forces of the black hole's gravitational pull, finally approaching the event horizon. According to Einstein's principle of equivalence, which is a cornerstone of general relativity, this moment should be uneventful. For the astronaut in freefall, crossing the invisible boundary should feel like nothing at all. There is no local sign, no sudden jolt, no special marker that says, "You are now entering the abyss." It's a smooth transition from one region of spacetime to another, at least from the astronaut's perspective. But the firewall hypothesis paints a very different, and far more violent, picture. To save the principle of information conservation from the clutches of Hawking radiation, some physicists have been forced to consider a shocking possibility. What if the event horizon is not smooth? What if instead it is a literal wall of fire? Not a metaphor, but a real, searing boundary made of incredibly high-energy particles. The theory suggests that just inside the event horizon, the quantum entanglement of particles, a phenomenon where two particles remain connected across space, is forced to break in a sudden and dramatic way. This violent severing of quantum links would release an enormous amount of energy, creating a blistering inferno. Anything or anyone crossing this threshold would not be gently pulled inward. They would be instantly vaporized, reduced to their fundamental particles long before the singularity could crush them. This creates a profound dilemma, a true paradox with no easy resolution. On one hand, we have the demands of quantum mechanics, which seem to require such a firewall to prevent information from being lost. If information is to be preserved and eventually radiated back out, it cannot fall deep into the black hole. It must be stopped or encoded at the boundary. The firewall acts as that cosmic shredder and encoder, destroying the object but preserving its information in the resulting energy blast. On the other hand, we have the beautiful and well-tested framework of general relativity, which insists that the event horizon must be uneventful. An astronaut falling into a large black hole should not even be able to tell when they cross the point of no return. The existence of a firewall shatters this principle. It means the universe has a special, deadly surface that violates the very rules Einstein's theory relies upon. So, what would be the actual fate of an astronaut approaching a black hole? The classical answer is spaghettification. As they fall feet first toward the singularity, the gravitational pull on their feet would be exponentially stronger than the pull on their head. This difference in force, known as a tidal force, would stretch their body into a long, thin stream of atoms, like a piece of spaghetti. This is a direct prediction of general relativity, and would happen well inside the event horizon for a large black hole. But if the firewall is real, there is no spaghettification. The astronaut would never get that far. The moment they touched the event horizon, they would be flash incinerated by a wall of energy hotter than the core of a star. We are thus left with two mutually exclusive predictions from our two most fundamental theories of physics. One says you are stretched apart. The other says you are burned to a crisp. They cannot both be correct. The firewall paradox forces us to confront the unsettling reality that our understanding of the universe might have a catastrophic flaw right at the edge of its most extreme objects. It is a stark reminder that when our most cherished physical principles collide, the result is not clarity, but a deeper, more fiery mystery. Building upon this violent conflict at the event horizon, we encounter a mystery that asks a fundamental question about the universe's very design. Does nature have a sense of decency? This idea is captured in the cosmic censorship hypothesis, a profound conjecture proposed by the Nobel laureate Roger Penrose. In essence, Penrose suggested that the universe possesses a kind of cosmic modesty, a built-in rule that prevents the utter chaos of a singularity from being visible to the outside world. It's the idea that nature always dresses a singularity by wrapping it in an event horizon, effectively hiding its infinite and lawless core from the rest of the cosmos. This event horizon acts as a one-way curtain, shielding the predictable universe we inhabit from the unpredictable physics that reigns supreme at the singularity. Without this censorship, the universe as we know it might not be able to function. But what if this cosmic censorship could be violated? What if a singularity could be stripped of its protective horizon? The result would be the most terrifying and bizarre object conceivable: a naked singularity. Imagine a point of infinite density where the laws of physics break down completely, just hanging out in the middle of space for everyone to see. It wouldn't be black. It would be exposed, a raw wound in the fabric of reality with no event horizon to contain its madness. The implications of such an object existing are staggering. At a naked singularity, prediction becomes impossible. Einstein's equations, which normally allow us to calculate the future evolution of a system from its initial conditions, would simply fail. The singularity could spit out anything at any time for no reason at all. It could violate causality, the principle that cause must always precede effect. An astronaut orbiting a naked singularity might witness events happening in reverse, or see an effect occur before its cause, rendering the very concept of time meaningless. The question of whether naked singularities can form is one of the most active areas of research in theoretical physics. The general belief, and the hope of many physicists, is that the cosmic censorship hypothesis holds true. When a star collapses, the process is thought to be so violent and messy that an event horizon always forms before the singularity can be revealed. However, mathematical models exploring certain types of collapse, particularly for rotating or electrically charged black holes, suggest that under very specific and extreme conditions, a naked singularity might indeed be possible. If a black hole were spinning at the absolute maximum possible rate, or possessed an enormous electric charge, the event horizon might shrink to a point of vanishing, leaving the singularity exposed. While these conditions may be extraordinarily rare in nature, the mere mathematical possibility forces us to confront what the universe would allow. Discovering a naked singularity would be a scientific revolution of the highest order. On one hand, it would be a nightmare for physics, as it would mean that there are places in the universe where the rule of law completely breaks down, making any prediction futile. On the other hand, it would be an unprecedented opportunity. A naked singularity would be a direct window into the realm of quantum gravity, allowing us to observe the effects of a theory we have not yet discovered. We wouldn't have to infer what happens at the center of a black hole. We could potentially see its influence on the space around it. The intense gravitational lensing and radiation emanating from such an object would carry the fingerprints of physics at its most extreme. The search for naked singularities is, therefore, not just a test of a mathematical hypothesis, but a quest to understand if the universe is fundamentally orderly, or if it permits islands of absolute chaos. It probes the very idea of whether the cosmos is a place that can be understood through science, or if there are corners where understanding itself is impossible. Leaving behind the theoretical firewalls and exposed singularities, we now turn our gaze to the true giants of the cosmos, objects whose very existence challenges our understanding of cosmic history. Nestled at the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not merely large black holes. They are behemoths containing the mass of millions, even billions of suns, all compressed into a region of space no larger than our solar system. Their dominance is clear, but their origin story is one of the greatest unsolved mysteries in modern astrophysics. The puzzle becomes truly profound when we look back in time. We have observed quasars, the intensely bright accretion disks of supermassive black holes shining from when the universe was less than a billion years old. This presents a monumental challenge. How did these gravitational monsters grow so unimaginably large, so incredibly fast? Astrophysicists are faced with two primary, competing theories, and both struggle to explain the rapid growth we observe. The first and more traditional idea is often called the bottom-up scenario. It suggests that the first generation of stars in the universe, known as population 3 stars, were colossal, perhaps hundreds of times more massive than our Sun. These giants would have lived fast and died young, exploding as supernova or collapsing directly to form stellar mass black holes, each weighing maybe 10 to 100 solar masses. According to this theory, these fledgling black holes then began a slow and steady growth process, merging with each other and voraciously consuming surrounding gas and dust over hundreds of millions of years. This gradual accumulation of mass would, in theory, eventually lead to a supermassive black hole. However, the clock of the early universe ticks loudly against this idea. There simply may not have been enough time for a small black hole to eat its way to supermassive status in less than a billion years. Imagine trying to fill a swimming pool with a garden hose. You can do it, but it takes a long time. Now imagine you only have a few minutes. That's the kind of timescale pressure we're talking about. There is a fundamental speed limit to how quickly a black hole can consume matter, known as the Eddington limit. If a black hole eats too greedily, The intense radiation from the infalling material actually pushes back against the incoming gas, preventing further growth. To reach billions of solar masses so quickly, these early black holes would have had to feed at or even above this theoretical limit for almost their entire lives, a sustained binge-eating feat that seems highly improbable. The severe limitations of the bottom-up approach have led many scientists to consider a more radical, top-down theory, direct collapse. This hypothesis proposes that the first supermassive black holes didn't start small at all. Instead, they were born big, in the dense, pristine environment of the early universe before the first stars had fully formed. Immense clouds of primordial gas could have collapsed under their own gravity directly into a black hole, bypassing the star phase entirely. This wouldn't create a mere 100 solar mass black hole. It would instantly create a seed black hole containing tens of thousands, perhaps even 100,000, times the mass of our Sun. With such a massive head start, this seed would have a much easier time growing to supermassive proportions within the tight time frame, as its immense gravity would allow it to pull in matter more efficiently. Yet, the direct collapse model has its own set of very specific requirements. For a giant gas cloud to collapse directly into a black hole, it must avoid fragmenting into many smaller stars along the way. To prevent this fragmentation, the gas cloud needs to be incredibly hot, which means it must be largely free of elements like carbon and oxygen that help gas cool down and clump together. This points to an environment of pure hydrogen and helium, which existed only in the very earliest epochs. Furthermore, the cloud would need to be bathed in a strong external source of ultraviolet light, perhaps from a nearby nascent galaxy, to keep the hydrogen from cooling. Finding evidence for these precise conditions in the early universe is an active pursuit, making direct collapse a compelling but difficult theory to confirm. A third, even more exotic possibility involves the dense primordial soup of the universe moments after the Big Bang. Could immense fluctuations in density have caused some regions to collapse directly into black holes? These so-called primordial black holes, if they formed with enough mass, could also serve as the seeds for the supermassive black holes we see today. The search for answers is driving the next generation of space telescopes. Instruments like the James Webb Space Telescope are peering back to the era of the first galaxies, hunting for the faint signatures of these infant supermassive black holes. By studying their light, we hope to weigh them and understand their feeding habits, gathering crucial clues to determine which path, slow growth from a small seed or catastrophic collapse from a giant cloud, nature actually chose to build the engines that power the centers of galaxies. But if the event horizon is a one-way street into a black hole, could there be a corresponding exit? This question leads us from the known horrors of singularities to the breathtaking possibilities of cosmic shortcuts and reverse universes. Einstein's field equations, which describe the fabric of space-time, are famously symmetrical with respect to time. This mathematical symmetry opens the door to a fascinating, though entirely theoretical, concept: the white hole. Imagine a black hole running in reverse. While a black hole is a region of space from which nothing can escape, a white hole would be a region to which nothing can enter. It would be a cosmic fountain, violently expelling all the matter and energy that a black hole has ever swallowed. It's as if the universe had a permanent playback button for gravity's ultimate trap. The idea is compelling, suggesting a potential cycle of cosmic digestion and rebirth. However, white holes face a monumental physical problem. They appear to violate the second law of thermodynamics, which dictates that entropy or disorder always increases. A white hole would essentially be a source of order, spewing out structured energy into the universe without any apparent cause, acting like a perpetual motion machine for spacetime. No observational evidence for a white hole has ever been found, and most physicists consider them to be mathematical artifacts rather than real celestial objects. Yet, Their theoretical existence is crucial because it connects directly to one of the most alluring ideas in science fiction and theoretical physics, the wormhole. Formerly known as an Einstein-Rosen bridge, a wormhole is conceived as a tunnel or shortcut through the fabric of spacetime. Picture the universe as a vast sheet of paper. To get from a point on the left side to a point on the right, you would normally have to travel all the way across the surface. But if you could fold the paper so the 2 points touch, a wormhole would be a tiny tunnel piercing through the fold, creating a direct pathway that could reduce a journey of millions of light years to just a few steps. In theory, a wormhole would connect the interior of a black hole, a point of immense gravitational crushing, to a white hole in another location, or even in another universe entirely. It would be the ultimate cosmic subway system. The challenge, and it is an enormous one, is stability. The wormholes predicted by Einstein's equations are not the stable, traversable tunnels we dream of. They are often referred to as non-traversable because they would snap shut instantly, faster than even a photon of light could travel through. The immense gravitational forces at the black hole singularity would collapse the tunnel in a fraction of a second, crushing anything that attempted the passage. To keep a wormhole open long enough for anything to traverse it, physics requires something truly exotic: matter with negative energy density, often called exotic matter. This isn't just antimatter. Antimatter has positive energy and would be gravitationally attracted to normal matter, only accelerating the wormhole's collapse. Exotic matter would possess a kind of anti-gravity, a repulsive force that could prop the wormhole's throat open against the relentless pressure of gravity. The search for such exotic matter leads us to another strange quantum phenomenon, the Casimir effect. In a vacuum, pairs of virtual particles constantly pop in and out of existence. If you place two incredibly smooth, uncharged metal plates extremely close together, you can restrict the kinds of virtual particles that can appear in the gap between them. This creates a subtle pressure difference, with more virtual particle activity outside the plates than inside, which actually pushes the plates together. In the narrow space between the plates, the energy density is lower than that of the surrounding vacuum. In a sense, this region has a negative energy density relative to its surroundings. While the amount of negative energy generated by the Casimir effect is infinitesimally small, it provides a tantalizing hint that the laws of quantum mechanics might permit the exotic matter needed for wormholes. The problem is scale. To stabilize a wormhole large enough for a person to pass through, you would need astronomical quantities of this negative energy, a technological and physical hurdle that seems insurmountable with our current understanding. Therefore, while white holes and wormholes are elegant solutions scribbled in the margins of Einstein's notebooks, they remain firmly in the realm of mathematical possibility. They are ghosts in the machine of general relativity, hinting at a universe far more interconnected and strange than we can perceive. Their study is not wasted effort, however. By pushing these ideas to their limits, physicists test the foundations of general relativity and explore the boundaries where it must eventually merge with quantum theory. For now, traversable wormholes are the stuff of dreams, but they continue to inspire us to ask whether the universe's most forbidden pathways might one day become routes for exploration. Pushing past the violent drama of the firewall and the theoretical possibility of wormholes, we arrive at a mystery that is perhaps the most profound of all, because it forces us to confront the ultimate meaning of inside. Once something crosses the event horizon, its fate, according to classical general relativity, is sealed. It will be drawn inexorably toward the central singularity, and in a finite amount of time be crushed out of existence. But what does that journey actually look like? And what, if anything, lies on the other side of that crushing endpoint? This is the mystery of the black hole interior, a realm forever shielded from our view, where even our most trusted theories can offer only wild speculation. From the perspective of an outside observer, the story seems tragically simple. Due to the extreme warping of time predicted by relativity, an object falling toward a black hole would appear to slow down as it approaches the event horizon, becoming increasingly redshifted until it fades from view entirely. It would look as though time for the falling object has stopped, freezing it forever on the threshold. But for the astronaut making the plunge, the experience is dramatically different. Assuming they avoid any hypothetical firewall, they would cross the event horizon without any local sensation, passing the point of no return completely unaware. Their journey inward, however, would quickly become a descent into a profoundly alien geometry. Inside the event horizon of a simple, non-rotating black hole, a radical shift occurs in the very nature of space and time. Outside the horizon, you can always choose not to move toward the center. You can orbit or fly away. Inside, the gravitational pull is so intense that the future itself is forced to point toward the singularity. In a mathematical sense, the roles of space and time swap. The direction toward the singularity ceases to be a choice in space and becomes your inevitable future. Every possible path, every particle, every photon, is doomed to travel along a trajectory that ends at the central point. There is no force in the universe that can prevent it. The astronaut isn't just being pulled. They are literally falling into their own future. A future that terminates at the singularity in a matter of seconds or hours, depending on the black hole's size. This is the classical picture, a one-way trip to oblivion. But what if the singularity is not an end, but a bridge? This is where the interpretations become extraordinarily speculative. Some solutions to Einstein's equations, particularly for rotating black holes known as Kerr black holes, suggest a more complex interior. Instead of a point-like singularity, a Kerr black hole may contain a ring singularity, a spinning loop of infinite density. The mathematics describing this ring singularity are even stranger than for a point, and they open up a dizzying possibility. If an object could somehow avoid being torn apart by immense tidal forces and gravitational shear, it might not be crushed at the ring. Instead, it might pass through it. And this is where the idea of a gateway emerges. Passing through the ring singularity of a theoretical Kerr black hole could lead to a region of spacetime that is completely disconnected from our own universe. This region, often called an other side, might be a separate universe entirely, with its own physical constants and laws of physics. Alternatively, it could be a distant part of our own universe, a wormhole-like connection creating a shortcut across cosmic distances. There is even a mathematical possibility of emerging into a white hole in another cosmos, as we discussed earlier, where all the accumulated matter of the black hole is explosively ejected. However, these tantalizing ideas are plagued with monumental problems. First, the region inside a Kerr black hole is thought to be violently unstable. Even the slightest perturbation, a single particle of dust falling in, could cause the interior geometry to collapse into a chaotic mess, likely sealing any hypothetical gateway or creating lethal gravitational shockwaves. Second, the gravitational forces near the ring singularity would be unimaginably complex, generating forces that would stretch and compress any object in multiple directions simultaneously, a process far more destructive than simple spaghettification. It is almost certain that any complex structure, let alone an astronaut, would be reduced to a stream of elementary particles long before reaching the ring. The most sobering interpretation, and perhaps the most widely accepted, is that these mathematical solutions describing gateways are simply artifacts of our idealized models. Real black holes are not the perfect vacuum solutions described by Kerr metrics. They are messy. They accrete matter, they have magnetic fields, and they are not in perfect isolation. When these real-world factors are considered, many physicists argue, the elegant interiors collapse into the classic, deadly crush of a singularity. The gateway may be a beautiful phantom in the equations, but not a feature of the actual universe. This leaves us in a state of profound ignorance. The interior of a black hole is the ultimate blind spot in our map of reality. We cannot observe it, and we cannot receive any information from it. Any theory about what happens beyond the singularity is, at present, untestable metaphysics. It exists in the realm of mathematical possibility, a playground for theorists to explore the furthest consequences of general relativity. The mystery of the other side forces us to acknowledge the limits of scientific inquiry. Some questions may simply have answers that are forever hidden behind a veil of infinite gravity, leaving us to wonder if the universe's greatest secrets are destined to remain just that, secrets. We have discussed the terrifying journey toward the singularity, but what happens at the very end of that journey? The fate of matter inside a black hole is a mystery that goes far deeper than the dramatic stretching of spaghettification. That process merely gets matter through the door. The true enigma is what occurs when it reaches the final destination. According to the classical picture from general relativity, the answer is horrifyingly simple: annihilation. Every atom, every fundamental particle, every bit of information that crosses the event horizon is doomed to be crushed into the infinite density of the singularity. It's as if the universe has a built-in shredder, one that doesn't just destroy the structure of an object, but obliterates the very particles that constitute it, leaving behind no trace of their original identity. But is this truly the end? The concept of infinite density is a major red flag in physics, a signal that our theory has broken down. This is where we must confront our profound ignorance about the final state of matter. Without a theory of quantum gravity, we are essentially guessing. One compelling possibility is that matter isn't crushed at all, but is transformed. Imagine the immense pressures and temperatures as matter is compressed near the singularity. Under such extreme conditions, the very distinction between matter and energy, as stated by Einstein's famous equation, might become blurred. Could the intense gravitational field act as the ultimate particle accelerator, smashing matter together with such force that it is converted directly into pure energy? This energy might then be radiated away as gravitational waves or somehow contribute to the Hawking radiation slowly leaking from the black hole. In this scenario, the black hole wouldn't be an eternal tomb, but a cosmic recycling plant, converting locked-up matter back into a form that can rejoin the universe. Another, even more radical idea comes from the holographic principle. If the information about what falls into a black hole is truly encoded on its two-dimensional event horizon, then perhaps the matter itself never actually travels to the center. Think of it like this. When you watch a movie on a flat screen, the three-dimensional actors aren't actually inside the television. The screen contains all the information needed to project the illusion of depth. In a similar way, the holographic principle suggests that the three-dimensional reality of an astronaut falling into a black hole is a projection from the information stored on the event horizon's surface. The infalling matter would hit this surface and be translated into a complex pattern of quantum data. From the perspective of the universe outside, the matter is smeared across the horizon. From the perspective of the astronaut, they continue falling inward. This creates a bizarre paradox of perspective, but it offers a way to avoid the destructive singularity entirely. The matter isn't destroyed, it's transformed into information. A third hypothesis involves the potential nature of a quantum singularity. Rather than a point of infinite density, a theory of quantum gravity might reveal that the center of a black hole is a dense, chaotic region often called a quantum bounce or a Planck star. In this model, the collapse of matter is halted by powerful repulsive quantum forces when it reaches the Planck scale, the smallest possible unit of length. The matter would be compressed to an unimaginable density, but not an infinite one. It would then rebound, much like a ball bouncing off a floor. However, because of the extreme warping of spacetime inside the event horizon, this bounce could take billions of years from an outside perspective. This would mean that what we perceive as a permanent black hole is actually a temporarily collapsed object, and the matter within is in a state of suspended animation, waiting to potentially re-emerge in the distant future. The truth is, we have no observational way to distinguish between these wildly different fates. Is matter annihilated, transformed, encoded, or just stored? Each possibility has profound implications. If matter is truly destroyed, it challenges the core laws of quantum physics. If it is transformed or encoded, it suggests a universe far more interconnected and holographic than we ever imagined. And if it is simply stored, it opens the door to the mind-bending idea that black holes could be potential gateways to new phases of the universe. The ultimate fate of matter inside a black hole is therefore not just a question about black holes. It is a question about the fundamental conservation laws of the cosmos and the final states that reality permits. Until we can peer beyond the event horizon with the laws of quantum gravity, the final moments of anything that falls into a black hole will remain one of the universe's most tightly guarded secrets. But if black holes can form from the collapse of stars, could they also be relics from the universe's very first moment? This leads us to a mystery that connects the largest cosmic structures to the smallest instance after creation: the potential link between black holes and dark matter. We know dark matter exists. We see its gravitational fingerprint in the way galaxies spin too fast to hold themselves together, and in the way immense clusters of galaxies bend light from objects behind them. This invisible substance makes up about 85% of all the matter in the cosmos, yet we have no idea what it is. For decades, the leading candidates have been exotic, undiscovered subatomic particles, like WIMP or actions. But what if the answer isn't a tiny particle, but a multitude of cosmic fossils? What if dark matter is, at least in part, made of black holes? Not the black holes we see today, born from dying stars, but something far older and more mysterious: primordial black holes. The theory proposes that in the extreme density and turbulence of the universe's first second, even its first fraction of a second, random fluctuations in density could have been so intense that pockets of space spontaneously collapsed under their own gravity. These wouldn't require a star's death. They would be a direct birth from the fiery energy of the Big Bang itself. A primordial black hole could form with almost any mass, from as light as a small asteroid to many times the mass of our Sun. And if they formed in vast numbers, they could be floating everywhere in space, invisible, their collective gravity providing the missing mass we attribute to dark matter. The appeal of this idea is its elegant simplicity. It uses a known gravitational object, a black hole, to explain a gravitational phenomenon, eliminating the need to invent an entirely new type of particle that has so far eluded every detector we've built. It also provides a natural candidate for the seeds of the supermassive black holes we find at the centers of galaxies. A large primordial black hole could have served as the ready-made core around which a galaxy grew. Furthermore, the concept received a significant boost with the first detections of gravitational waves. Some of the black hole mergers observed by LIGO and Virgo involved black holes of a mass that is somewhat unexpected from standard stellar evolution, reigniting interest in a primordial origin for at least some of these objects. However, for this idea to hold water, primordial black holes must be able to survive for 13.8 billion years, and their numbers must match the precise distribution of dark matter we observe throughout the cosmos. This is where the theory faces severe challenges, primarily from the phenomenon of gravitational microlensing. The concept is straightforward. If a massive, compact object like a primordial black hole were to pass directly between us and a distant star, its gravity would act as a lens, bending the starlight and causing the star to temporarily appear brighter. By monitoring millions of stars in nearby galaxies, like the Large and Small Magellanic Clouds, astronomers have conducted extensive surveys searching for these telltale flashes. The results have severely constrained the possibility that primordial black holes within a certain mass range could make up all of dark matter. For instance, if dark matter were composed of black holes around the mass of our Sun, we would expect to see a large number of these microlensing events. We simply don't see enough. The constraints are like a series of windows being slammed shut. Observations have ruled out primordial black holes over a wide mass spectrum, from about the mass of a large asteroid up to about 100 times the mass of our Sun, as being the primary component of dark matter. There are, however, two intriguing windows that remain open. The first is for very low mass black holes, sometimes called asteroid mass black holes. These would have been so small that they would have evaporated by now due to Hawking radiation, unless they were formed with just the right mass to have survived. The second, and perhaps more compelling, window is for much larger objects, black holes in the intermediate mass range from about 1,000 to 100,000 solar masses. These would be too massive and rare to produce frequent microlensing events, yet numerous enough to possibly account for a significant fraction of the dark matter gravitational pull in galactic halos. The implications of this being true would be revolutionary. It would mean that dark matter isn't an exotic particle field, but a population of ancient, discrete objects. It would reshape our understanding of the early universe, suggesting that its first moments were far more chaotic and lumpy than our standard models predict. The search for evidence continues, with astronomers using every tool at their disposal, from studying the subtle distortions in the cosmic microwave background to analyzing the precise timing of signals from pulsars. The connection between black holes and dark matter remains a tantalizing what if, a ghost of a possibility haunting the edges of cosmology. It exemplifies the creative ways scientists are trying to solve the universe's biggest puzzles, demonstrating that sometimes the answer to a profound mystery might be hiding in plain sight, not as a swarm of invisible particles, but as a sky full of ancient dark shadows. Now, if information is not lost but is somehow preserved at the boundary, this leads us to one of the most radical and mind-altering concepts in all of modern physics, the holographic principle. To grasp this idea, let's start with a familiar object, a hologram. On a credit card, you see a shimmering, three-dimensional image that seems to have depth and solidity. But that image isn't truly three-dimensional. It's encoded on a flat, two-dimensional piece of plastic. All the information needed to create the illusion of a 3D object is contained on that 2D surface. The holographic principle applies this same logic to the entire universe, suggesting that our perception of a rich, three-dimensional reality might be a magnificent illusion, a projection from a two-dimensional surface at the very edge of space. This astonishing idea was born directly from the thermodynamics of black holes. In the 1970s, physicist Jacob Bekenstein made a revolutionary connection. He realized that a black hole's event horizon has entropy. Entropy is a measure of disorder, or more precisely, the number of ways a system's microscopic parts can be arranged. A black hole with a larger event horizon has more area, and Bekenstein showed that its entropy is proportional to that area. This was deeply puzzling. In ordinary systems, entropy is proportional to volume. A larger box can contain more disordered arrangements of particles than a smaller box. But for a black hole, the ultimate container, the entropy depends on its surface area, not the vast volume it encloses. This hinted at a profound secret. Perhaps all the information about everything inside a black hole is not contained within its three-dimensional interior, but is instead smeared across its two-dimensional boundary, the event horizon. This insight was refined by Gerard T. Hooft and Leonard Susskind into the full holographic principle. They proposed that the maximum amount of information that can possibly be stored in any region of space is not determined by its volume, but by the area of its boundary. To understand how strange this is, imagine a room. You would naturally think you could fill that room with hard drives, and the amount of data you could store would depend on how many drives you could fit inside the volume. The holographic principle says no. It claims the ultimate information storage limit for that room is determined by the surface area of its walls, floor, and ceiling. It's as if the entire contents of the room, the chairs, the air, the people, are actually just a projection from the walls themselves. In this view, our three-dimensional universe is like the movie on the screen, and the true, fundamental reality is the two-dimensional data encoded on a cosmic surface at the limits of perception. Applying this to a black hole provides a potential solution to the information paradox. When an object falls in, it doesn't journey to the singularity to be destroyed. Instead, its information is instantly translated into a complex, scrambled pattern on the event horizon, increasing its entropy. This is often described as the information being painted onto the surface. Then, as the black hole slowly evaporates via Hawking radiation, this encoded information is gradually and chaotically released back into the universe. The information was never truly lost. It was just stored in a radically different format, much like the information in a 3D movie file is stored on a flat DVD. The holographic principle saves quantum mechanics by redefining where and how reality is fundamentally written. But the implications are far grander than just black holes. If this principle holds for these gravitational extremes, it might be a fundamental property of the universe. We could all be living inside a cosmic hologram. The world we experience with its depth, texture, and solidity would be a tremendously detailed and convincing projection from a two-dimensional shell at the edge of the observable universe. This doesn't mean reality is an illusion in the philosophical sense. The tables we bump into are still solid, but it suggests that the most fundamental level of reality, the Planck scale where space and time themselves are quantized, might be two-dimensional. Our third dimension, and with it the passage of time, emerges from the complex interactions of quantum bits of information on that distant boundary, much like the temperature of a gas emerges from the chaotic motion of countless molecules. This idea turns our classical intuition about space and dimensionality completely on its head. For centuries, we've assumed that reality is fundamentally three-dimensional. The holographic principle challenges that at the most basic level, suggesting that the universe is a holographic display of staggering complexity. While it remains a highly theoretical framework, it represents a monumental shift in how physicists think about the nature of space, time, and information. It's a direct consequence of taking black holes seriously, demonstrating that these cosmic anomalies are not just curiosities. They are portals to a deeper understanding of reality itself, forcing us to question the very stage upon which the drama of the cosmos plays out. This elegant simplicity leads us to our next great puzzle, a concept that seems almost too good to be true, the no-hair theorem. In the bewildering complexity of the cosmos, black holes stand out as paragons of minimalism. Imagine any object you know, a planet, a star, even a person. Each is incredibly complex, defined by countless properties: composition, temperature, magnetic fields, surface features, and a nearly infinite amount of information about their history and structure. Now, consider a black hole. According to this theorem, once the turmoil of its formation settles down, every single black hole in the universe can be completely and uniquely described by just three, and only three, numbers: its mass, its electric charge, and its angular momentum or spin. That's it. Mass tells you how much it weighs, spin how fast it's rotating, and charge its electrical properties. The theorem's charming nickname, no hair, implies that black holes have no other distinguishing features, no frizz or flare, no individual hair to tell them apart. Two black holes with identical mass, charge, and spin are perfect twins, utterly indistinguishable from one another, regardless of what they were made from. Whether it formed from a collapsed star made of pure hydrogen or from a compressed sphere of antique furniture, the resulting black hole would be exactly the same. This idea is a direct consequence of the powerful force of gravity and the nature of the event horizon. The theorem suggests that when a star collapses to form a black hole, an incredible act of cosmic forgetting occurs. All the intricate details about the matter that fell in, the type of atoms, their arrangement, the complex magnetic fields, even whether the star was made of matter or antimatter, are entirely lost. The black hole mercilessly shreds any individuality, erasing a rich history of information and leaving behind only 3 bare, sterile numbers. It's the ultimate universal baldness. This profound simplicity is what makes black holes such powerful theoretical tools. They are the simplest macroscopic objects in the universe, and their behavior is governed by a few clean equations. However, the real world is rarely so simple, and physicists have long questioned whether this beautiful theorem is an absolute truth or just a very good approximation. The search for potential hair on black holes ways the no-hair theorem might be violated is a major frontier in gravitational physics, one of the most promising avenues for giving a black hole a more complex hairstyle involves quantum fields. In the 1970s, theorist Werner Israel, a key architect of the no-hair theorem, himself explored how fields like the electromagnetic field might cling to a black hole in a stable configuration, creating a kind of soft hair. This wouldn't be hair made of matter, but hair made of persistent field lines that are somehow pinned to the horizon, potentially storing tiny bits of information about what fell in. More recently, the work of Stephen Hawking, Malcolm Perry, and Andrew Strominger revived this idea with a specific proposal. They suggested that a black hole could be surrounded by an infinite number of these soft quantum hairs, generated by zero-energy particles, or soft photons and soft gravitons, existing at the event horizon. These particles carry incredibly low, almost infinitesimal energy, but they could subtly change the geometry of the horizon, encoding information about the black hole's past in a way that doesn't affect its mass, charge, or spin in any significant way we can currently measure. It's as if the black hole's smooth surface is covered in a faint, holographic fuzz, a delicate memory of everything it has consumed. Another pathway to hairy black holes comes from the realm of exotic matter and theories beyond the standard model. What if there are types of particles or fields that we haven't yet discovered that don't behave like the ones we know? Certain hypothetical fields, like scalar fields predicted by some string theory models, might not be absorbed or radiated away as easily as normal matter. Instead, they could form stable clouds around a black hole, creating a permanent, observable hairdo. These configurations are known as boson stars or scalar field hair. Imagine a black hole wearing a giant, invisible wig made of a mysterious quantum field. This hairy configuration would make the black hole distinguishable from a bald one, violating the pure letter of the no-hair theorem and providing a visible signature of new physics. The implications of finding hairy black holes would be revolutionary. It would mean that black holes are not the simple, forgetful objects we thought they were. They might retain some memory of their formation, offering a way to peer into their history. More importantly, it could provide a natural mechanism for solving the information paradox. If information isn't lost inside the singularity, but is instead preserved in the intricate hairstyle of the horizon, then the conflict between general relativity and quantum mechanics could be resolved. The hunt for evidence is on. Gravitational wave observatories like LIGO and Virgo are meticulously analyzing the ring-down phase of black hole mergers, the final moments when the newly formed black hole shakes like a bell before settling into a quiet state. The frequencies of these gravitational waves are determined by the black hole's mass and spin alone. If any deviations from the predictions of the no-hair theorem are detected in this ring-down, it would be a smoking gun for physics beyond Einstein, a clear sign that black holes have a more complex and interesting personality than we ever imagined. This discovery that black holes have entropy was a bombshell that completely reshaped our understanding of thermodynamics and gravity. To grasp why it's so revolutionary, we need to step back and consider what entropy really means. In everyday terms, entropy is often described as a measure of disorder. A tidy room has low entropy. A messy room has high entropy. But in physics, it's more precise to think of entropy as a measure of the number of ways the microscopic components of a system can be arranged while still looking the same from the outside. A pristine ice cube has low entropy because its water molecules are locked into a very specific, orderly crystal lattice. When that ice cube melts into a puddle of water, the molecules can swirl and arrange themselves in a vast number of different configurations, and the puddle still looks like a puddle. The entropy has increased dramatically. Crucially, for any ordinary object, a gas, a star, a book, the maximum possible entropy it can contain is proportional to its volume. A bigger box can hold more disordered arrangements of atoms than a smaller box. This is why Jacob Bekenstein's realization in the 1970s was so utterly perplexing. He argued that a black hole must have entropy, and a tremendous amount of it. But this entropy wasn't proportional to the black hole's volume. It was proportional to the surface area of its event horizon. Think about how strange that is. You have this colossal object containing the mass of millions of stars, with a vast interior volume. Yet, according to the laws of thermodynamics, the total amount of information or disorder it can contain is determined not by how much space is inside it, but by the size of its two-dimensional boundary. It's as if the ultimate filing cabinet for cosmic disorder isn't the cabinet itself, but the paint on its outside surface. This area law for entropy was the first major clue that black holes might be fundamentally different from any other object in the universe, hinting that their true nature might be playing out on a surface, not within a volume. This profound link between area and entropy immediately fueled the development of the holographic principle, but it also presents a deep and ongoing mystery. If black holes have entropy, what are the microscopic ingredients that give rise to it? For a gas, the entropy comes from the countless different ways its molecules can be moving and positioned. For a black hole described only by its mass, charge, and spin, what are the underlying parts that can be rearranged to create such an immense value for disorder? The search for the microscopic source of black hole entropy is a direct path to a theory of quantum gravity. The most promising answer comes from the quantum nature of spacetime itself. Just as a material is made of atoms, many physicists believe that space may have a discrete, granular structure at the tiniest possible scale, the Planck length. In this view, the event horizon isn't a perfectly smooth surface. Instead, it might be a vibrant tapestry woven from individual, quantized units of area, tiny, fundamental pixels of spacetime. Theorists working on loop quantum gravity, for instance, have calculated that these elementary quanta of area on the horizon can exist in different quantum states. The immense entropy of the black hole then comes from the astronomical number of ways these microscopic Planck area units can be configured while still giving the black hole the same total mass and spin from the outside. It's analogous to the pixels on a computer screen. A black screen and a white screen might have the same number of pixels, but a screen displaying a detailed, complex image has those pixels arranged in a specific, information-rich pattern that corresponds to a lower entropy state than the random, high-entropy snow of a broken television. The black hole's entropy is the number of ways its horizons, pixels, can be arranged to look like a featureless black sphere to a distant observer. This perspective transforms the black hole from a classical sinkhole into a complex quantum system. The event horizon is not a passive boundary but an active, vibrating membrane composed of these fundamental units. This idea provides a beautiful, though still theoretical, explanation for the area entropy law. It suggests that the information about what fell into the black hole isn't lost inside a singularity, but is meticulously encoded in the specific quantum state of each and every one of these tiny Planck area building blocks on the horizon. The black hole's entropy is the logarithm of the number of possible quantum states its horizon can be in. This incredible density of information, the fact that all the complexity of a three-dimensional star can be stored on a two-dimensional surface, is the core of the holographic mystery. It forces us to consider that the true degrees of freedom of our universe might be living on a distant boundary, and that everything we see and experience, from the flight of a bird to the spin of a galaxy, is a magnificent and incredibly detailed projection from a simpler, lower-dimensional reality. While the ideas of firewalls and holographic encoding dance around the edges of the event horizon, a more direct challenge to the classical singularity comes from a theory that attempts to quantize the very fabric of space and time. This is the Planck star hypothesis, a fascinating proposal born from the framework of loop quantum gravity. Instead of accepting the terrifying infinite density predicted by Einstein's equations, this hypothesis offers a radical alternative, a cosmic rebound. The central idea is that the collapse of a star does not end in a catastrophic, lawless singularity. Instead, the incredible density and pressure trigger a powerful quantum repulsive force, a kind of cosmic spring that halts the collapse at the very last possible moment. To understand this, we need to think about the quantum nature of reality. In the subatomic world, everything is granular. Energy comes in packets, light comes in photons, and according to loop quantum gravity, space itself is not a smooth, continuous canvas. It is woven from a fabric of tiny, finite loops. These loops define a fundamental smallest possible unit of volume, a true pixel of space at the Planck scale. This granularity provides a natural brake on gravitational collapse. As matter is compressed to densities trillions of times greater than a neutron star, it reaches a point where it cannot be squeezed any further. The quantum structure of space itself pushes back, preventing matter from being crushed into an infinite point. The result is not a singularity but a Planck star, an object of staggering yet finite density compressed to about the size of the Planck length. This resolves the most profound mathematical headache of general relativity by simply erasing the infinity. The laws of physics need not break down because there is no point of infinite curvature. The journey of matter has a well-defined, albeit extreme, endpoint. But the implications of this hypothesis are even more spectacular than just avoiding a mathematical error. If the collapse is halted, what happens next? The theory suggests a bounce. The immense repulsive force generated at the moment of maximum compression does not just stop the collapse, it reverses it. The matter that was falling inward rebounds and begins to expand again. It's as if the dying star, instead of vanishing into a black hole, becomes the seed for a new phase of existence. However, from our perspective outside the black hole, this rebirth would be almost imperceptibly slow. Due to the extreme warping of time near the event horizon, the bounce would be dramatically stretched out. A process that might take only microseconds from the perspective of the infalling matter could take billions or even trillions of years from our viewpoint in the external universe. This leads to a truly mind-bending possibility. What we perceive as a permanent, eternal black hole might actually be a temporarily trapped region of spacetime. After an unimaginable cosmic age, the rebounding matter would eventually push back against the event horizon. When it does, the black hole would effectively transform into its theoretical opposite, a white hole. The event horizon, once a one-way membrane, would become a gateway for the trapped matter and energy to explosively re-enter our universe. Imagine a black hole that has been quietly sitting at the center of a galaxy for eons, slowly accreting matter. Then, trillions of years from now, long after all the stars have died, it suddenly lights up like a cosmic firework, spewing out everything it had ever consumed. This white hole phase would be brief and violent, a final act of cosmic recycling. While this sounds like a neat solution, the Planck star hypothesis faces significant challenges. The primary hurdle is that the interior of a black hole is expected to be highly unstable. Even minor irregularities in the collapsing matter or interactions with infalling material could disrupt the delicate quantum bounce, causing it to collapse chaotically into a singularity after all. Furthermore, since the predicted lifetimes of these objects are far longer than the current age of the universe, we have no way to directly observe one undergoing a bounce. For now, the Planck star remains a beautiful and compelling possibility, a testament to the power of theoretical physics to imagine a universe where even gravity's ultimate victory is only temporary, and where every end may contain the seed of a new beginning. This paradox, which we now know as the firewall, presents an agonizing choice between two pillars of physics, but it was the work of four physicists Almary, Marolf, Polchinski, and Sulker that sharpened this dilemma into an even more precise and devastating logical trap. Their formulation, known as the Amps paradox, doesn't just highlight a problem. It constructs a labyrinth with no apparent exit, forcing us to question a concept we often take for granted: where things are in space. The Amps argument starts by taking the principles of quantum mechanics more seriously than ever before, particularly the idea of entanglement. To understand it, we need to revisit the fate of a pair of entangled particles. Imagine we create two particles, A and B, that are quantumly entangled, meaning their fates are inextricably linked. Now we perform a cruel cosmic experiment. We throw particle A into a very old black hole, one that has been evaporating for a long time and is emitting Hawking radiation. Particle B remains safely outside with us. According to quantum mechanics, this Hawking radiation itself must be entangled with the interior of the black hole. It has to be, because it's created from the vacuum fluctuations at the event horizon. So, the Hawking radiation particle, let's call it C, is entangled with whatever is inside, including our infalling particle A. But here's the catch. Quantum mechanics has a fundamental rule called the monogamy of entanglement. A single particle cannot be fully entangled with two different systems at the same time. It's like a marriage. You can't have two spouses with equal commitment. Particle A is already deeply entangled with its original partner, particle B, back in our lab. For the theory to be consistent, particle A inside the black hole cannot also be entangled with the Hawking radiation, particle C outside. There's a conflict. This is where Amps present their devastating logical fork in the road. They argue we have only three choices, and each one leads to a profound violation of established physics. The first option is that the entanglement between the infalling particle A and its original partner B is broken as particle A crosses the horizon. But this would be a violent, non-local event, a sudden severing of quantum links. This act would release a tremendous amount of energy, creating the infamous firewall that vaporizes anything trying to enter. This saves the purity of the Hawking radiation, but destroys the principle of equivalence, the cornerstone of general relativity that says crossing the horizon should be uneventful. The second option is that the entanglement between particle A and B remains intact, meaning the entanglement between the Hawking radiation C and the black hole interior is somehow fake or transferred. But if the radiation is not truly entangled with the interior, then the radiation is just random thermal noise. And if the radiation is random, then the information about what fell into the black hole is lost forever when the black hole evaporates, violating the fundamental quantum law that information must be preserved. We are back to the original information paradox. The third and most radical option is that both entanglements are somehow preserved, cleverly avoiding the monogamy rule. But this would require a direct and paradoxical link between the interior of the black hole and the distant radiation, a connection that defies our understanding of locality, the principle that objects can only be influenced by their immediate surroundings, not by things that are far away. This would mean that the universe is fundamentally non-local in a way that makes a mockery of space itself. The Amps paradox, therefore, forces a choice that seems to demand we sacrifice one of three cherished principles: the smoothness of spacetime, the conservation of information, or the locality of physical interactions. This is the essence of black hole complementarity, a concept inspired by the quantum principle of complementarity, where two seemingly contradictory descriptions can both be true depending on the observer's perspective. The idea is that the viewpoint of an observer outside the black hole and the viewpoint of an observer falling in are both correct, but they can never be compared. From the outside, the information is encoded on the horizon and slowly radiated away. From the inside, the astronaut falls smoothly to their doom. The two descriptions are complementary, like the wave and particle nature of light. The catastrophe only occurs if you try to reconcile both perspectives into a single, objective reality, which the paradox suggests might be impossible. This forces a radical rethink of locality. Perhaps in the presence of such extreme gravity, our everyday notion that events happen at a specific point in space breaks down. Information might not be located in one place, but spread out or shared across vast distances in a way that is only apparent when we consider the quantum properties of gravity. The Amps paradox is not just a puzzle about black holes. It is a powerful lens focusing on the fault line between our two great theories of reality. It tells us that our comfortable assumptions about where things are and how they influence each other may be naive approximations that completely fail at the edge of a black hole, pointing toward a deeper, more interconnected, and far stranger description of the cosmos waiting to be discovered. While the event horizon marks a point of no return for matter falling inward, some of the most dramatic and energetic displays in the universe actually blast outward from the poles of black holes. These are relativistic jets, and their origin is one of the most spectacular unsolved mysteries in high-energy astrophysics. Imagine a fountain of energy so powerful that it shoots out from the vicinity of a black hole at nearly the speed of light, stretching for thousands, even millions, of light years across intergalactic space. These jets are not gentle streams. They are cosmic blowtorches, capable of punching through entire galaxies and influencing the formation of stars on a colossal scale. The sheer power involved is almost incomprehensible, often rivaling the combined light of every star in a galaxy, all focused into two narrow, opposing beams. We observe these jets predominantly in two types of systems. The first is in active galactic nuclei, where a supermassive black hole is actively feeding on a vast disk of gas and dust. The second is in smaller, stellar mass black holes within our own galaxy that are siphoning material from a companion star. In both cases, the presence of a hot, swirling accretion disk seems to be the key ingredient. The leading theoretical model for how these jets form is a breathtaking interplay between gravity, rotation, and magnetism. As material in the accretion disk spirals inward at tremendous speeds, it becomes an intensely hot, ionized plasma, a sea of charged particles. This plasma is coupled with incredibly powerful magnetic fields that are frozen into the disk and wound up tightly by its rapid rotation. Think of it like twisting a rubber band. As the disk spins, it drags the magnetic field lines along with it, twisting them into a tightly coiled, helical structure that points away from the black hole's poles. This creates a powerful magnetic slingshot. The immense pressure and energy near the inner edge of the accretion disk propels some of this charged plasma along these twisted field lines, channeling it into a focused beam that erupts from the polar regions. It's a natural particle accelerator on a cosmic scale, where magnetic forces can fling material to relativistic velocities. In some models, the black hole's own spin is the ultimate engine, powering the jet by interacting with the magnetic fields in a region of spacetime just outside the event horizon, known as the ergosphere, where nothing can remain stationary. However, while this general picture is widely accepted, The devil is in the details, and those details remain deeply mysterious. We still do not know the precise launching mechanism. Where exactly along the disk, or how close to the event horizon, does the jet actually originate? Is it from the inner regions of the accretion disk itself, or is the black hole's spin, via a process called the Blandford-Zeenagic mechanism, the primary driver? Furthermore, the process of particle acceleration is poorly understood. How are individual electrons and protons within the jet accelerated to such fantastic speeds, gaining energies billions of times greater than what our most powerful particle colliders on Earth can achieve? Shocks within the jet likely play a role, acting like cosmic surfboards that particles ride to incredible energies, but the exact process is a subject of intense debate. The jets themselves are also full of surprises. They are not smooth beams but often show a lumpy, knotted structure, suggesting that the ejection process is not steady but occurs in powerful, episodic bursts. Even more puzzling is the fact that not all black holes with accretion disks produce these jets. What special combination of factors the black hole's spin rate, the strength and configuration of the magnetic field, the rate of accretion triggers this incredible cosmic fireworks display? Answering these questions is crucial because black hole jets are not just fascinating curiosities. They are major players in cosmic evolution. By injecting enormous amounts of energy into their surroundings, they can regulate the growth of galaxies, heat the intergalactic medium, and stifle the birth of new stars. Understanding jets means understanding one of the most powerful feedback mechanisms the universe has ever devised. We have marveled at the stellar mass black holes born from dying stars and the supermassive giants that rule the centers of galaxies. But between these two known classes lies a vast and puzzling gap. This is the hunt for the missing link: intermediate mass black holes. Imagine a black hole that is neither a mere 10 times the mass of our Sun, nor a million, but something in the range of hundreds to hundreds of thousands of solar masses. These objects would be the crucial middle child in the black hole family tree, and finding them is essential for understanding how the supermassive behemoths could have grown so large so quickly in the early universe. Do they form as the initial seeds that then merge and feed? Or are they built from the bottom up through a different, more violent process? For decades, the evidence for their existence was frustratingly circumstantial. But recent breakthroughs are finally bringing these elusive objects out of the shadows. Some of the most compelling clues come from the study of incredibly bright X-ray sources found not in galactic centers, but out in the star-packed globular clusters that orbit galaxies like our own. These are known as ultraluminous X-ray sources, or ULCs. A typical stellar mass black hole pulling material from a companion star emits a certain amount of X-ray radiation, governed by its size and the rate it can feed. But ULXs are different. They shine with a brilliance that is hundreds or even thousands of times greater than what should be possible for a simple stellar mass black hole. The most straightforward explanation is that we are seeing a more massive object at work. If the engine is an intermediate mass black hole, its larger event horizon and stronger gravity would allow it to pull in and heat up more material, generating the extraordinary X-ray luminosity we observe. It's like the difference between a campfire and a blast furnace. The intense output points to a fundamentally more powerful source. However, the case isn't entirely closed. Some astrophysicists argue that these ultraluminous emissions could be explained by stellar mass black holes that are beaming their radiation, focusing it into a narrow jet that happens to be pointed directly at us, making them appear much brighter than they truly are. This debate has made the hunt for intermediate mass black holes a careful process of eliminating other possibilities. The case grew significantly stronger with the detection of gravitational waves. The LIGO and Virgo observatories have not only confirmed the existence of black holes, but have also begun to weigh them precisely. In 2019, a signal designated GW19052 one revealed something extraordinary: a black hole merger where the final product was about 142 times the mass of our Sun. This was a landmark event because the resulting object falls squarely into the intermediate mass range. Even more intriguingly, one of the two black holes that collided was about 85 solar masses, which is itself a mass that is difficult to explain through standard stellar collapse. This event provided the first direct, dynamical evidence that black holes in this intermediate mass range not only exist but can form through the merger of smaller black holes. It was a smoking gun, captured in the ripples of spacetime itself. But how do these missing links form in the first place? The runaway collision model is a leading and dramatic theory, particularly for the globular clusters where they are often sought. Picture a dense, ancient cluster of hundreds of thousands of stars, all orbiting each other in a tight gravitational dance. In this celestial mosh pit, the most massive stars would naturally sink to the center of the cluster through a process called dynamical friction. There, they could collide and merge, building up a supermassive star far larger than any that could form in isolation. This stellar behemoth would then live a short, violent life before collapsing directly into an intermediate mass black hole. This seed black hole could then continue to grow by consuming other stars or merging with other smaller black holes that also drifted to the cluster's core. It's a bottom-up process, but one that is dramatically accelerated by the extreme social environment of a star cluster, providing a potential pathway to create a black hole of a few hundred or a few thousand solar masses relatively quickly. An alternative, and perhaps complementary, idea is that intermediate mass black holes are actually the primordial seeds we discussed earlier. If the early universe created a population of black holes with masses around 1,000 suns, these objects would be the perfect building blocks for the supermassive black holes we see today. They would have the gravitational pull to quickly attract gas and merge with each other, efficiently growing to galactic scales within the universe's first billion years. Some of these primordial seeds might have wandered through intergalactic space without becoming the center of a large galaxy, remaining as free-floating intermediate mass black holes to this day. The ongoing search involves peering into the hearts of dense star clusters with powerful telescopes, looking for the subtle gravitational influence these objects have on the motions of nearby stars. Each new candidate, each unusual X-ray source, and each unique gravitational wave signal brings us closer to confirming this missing chapter in the black hole story, revealing the middleweights that could be the key to understanding the giants. Galaxies are not isolated islands in the cosmos. They are social creatures, drawn together by gravity in a slow, majestic dance that can last billions of years. When two galaxies collide, it is a spectacle of cosmic proportions, but it's not primarily the stars that crash together. The distances between them are so vast that they typically pass right by. Instead, the real drama unfolds at the very heart of each galaxy, where their supermassive black holes reside. As the galaxies merge, their central black holes are dragged by gravity toward the new common center of mass. They begin to orbit each other, forming a binary pair, a gravitational couple locked in a tightening embrace. According to Einstein's theory, such a duo should be a potent source of gravitational waves, and as they spiral inward, they would eventually collide in a cataclysm that shakes the very fabric of spacetime. We've witnessed these mergers for stellar mass black holes with LIGO and Virgo, so the process seems straightforward. But for the supermassive giants, there's a catch, a mysterious stumbling block known as the final parsec problem. The problem arises because of the way black holes lose orbital energy. In the early stages of the galactic merger, the black holes are surrounded by a dense swarm of stars. As they swing past these stars, they transfer some of their orbital energy to them through complex gravitational interactions, a process known as dynamical friction. This causes the black hole's orbit to shrink. However, as the orbit gets smaller, the black holes clear out their immediate vicinity. They either fling the surrounding stars away on high-speed trajectories or absorb them, creating a relative emptiness around the binary pair. Once their separation shrinks to about 1 parsec, roughly 3.26 light-years, they run out of stars to interact with. With no more gravitational brakes to apply, their inward spiral should, in theory, grind to a halt. They become stranded, orbiting each other for timescales longer than the current age of the universe, never quite reaching the point where gravitational wave emission becomes efficient enough to drive them to merger. This is the final parsec problem, a cosmic traffic jam that seems to prevent the universe's largest black holes from completing their gravitational dance. Yet, the universe clearly finds a way. The very existence of supermassive black hole binaries and the fact that we see supermassive black holes in the centers of all large galaxies, which are themselves the products of numerous mergers, is strong evidence that this problem is solved. The question is, how? Astronomers have proposed several compelling mechanisms to push these reluctant partners over the final hurdle. One of the leading solutions involves the presence of a massive, circumbinary disk of gas. If the merging galaxies are gas-rich, vast amounts of material can funnel toward the central binary. This gas doesn't just fall in passively. It can act as a dynamic mediator. As the black holes orbit, they create gravitational wakes in the gas disk, like speedboats carving troughs in water. These wakes exert a drag force on the black holes, sapping their orbital energy and angular momentum and causing their orbits to decay further. In some models, the gas can even lead to the formation of mini-disks around each black hole and a larger, encompassing disk, creating a complex gravitational system that efficiently drives the binary toward its inevitable collision. Another fascinating possibility involves introducing a third actor to the drama, a third supermassive black hole. In a major galactic merger, it's not just two galaxies coming together. Smaller satellite galaxies with their own central black holes could be involved. If a third black hole is thrown into the mix, the dynamics become chaotic and unpredictable in a process known as the gravitational slingshot. The three black holes engage in a complex gravitational dance, where close encounters can lead to one of them being ejected from the galaxy entirely at high speed, becoming a rogue black hole wandering the intergalactic void. But in the process, the gravitational interactions transfer energy in such a way that the remaining binary pair is left with a much tighter orbit, easily crossing the final parsec barrier. This three-body interaction is a violent but effective solution to the problem, a gravitational game of billiards where the payout is a merger-ready binary. The recent dawn of gravitational wave astronomy offers the most promising path to solving this mystery. While our current ground-based detectors are not sensitive to the low-frequency waves from supermassive black hole binaries, future space-based observatories like the Laser Interferometer Space Antenna, or LISA, are being designed for exactly this purpose. LISA will be able to hear the low, rumbling hum of these circling giants across cosmic distances. By carefully measuring the gravitational wave signal from a binary system, we could discern the environment in which it resides. The precise pattern of the waves would reveal whether the black holes are spiraling together through interaction with a gas disk, which would leave a specific fingerprint on the signal, or if they are evolving in a relatively star-poor environment, pointing toward a different solution. The detection of a background hum of gravitational waves from all the supermassive black hole binaries in the universe would tell us how common these mergers are and, by extension, how efficiently the final parsec problem is solved throughout cosmic history. This mystery is not just about the fate of two black holes. It's about understanding the life cycle of galaxies themselves and how the universe orchestrates the most massive collisions imaginable. But if the event horizon truly is the smooth, unremarkable boundary that Einstein's theory predicts, then the gravitational waves from a black hole merger should tell a very specific story. When two black holes spiral together and merge, the resulting cataclysm sends ripples through spacetime itself. In the final moments, the new, single black hole is born ringing like a bell, vibrating in a set of characteristic frequencies that quickly fade away as it settles into a quiet, stable state. This phase is called the ring-down, and according to classical general relativity, the frequencies of these gravitational waves are determined solely by the black hole's final mass and spin. The event horizon acts as a perfect, one-way membrane, and the waves should simply decay without a trace. There should be no encore. However, a controversial and thrilling idea suggests that this classical picture might be incomplete, and that the gravitational wave signal might contain a faint, repeating whisper and echo from the edge of reality. The theory behind these proposed echoes challenges the very nature of the event horizon. If the horizon is not a perfect void, but has some kind of physical structure just outside or even replacing it, then it could act as a partially reflective surface. What could this structure be? One possibility is the infamous firewall, that blistering wall of high-energy particles. Another, more subtle idea is that quantum gravity effects endow the horizon with a fuzzy, quantum structure, turning it from a smooth mathematical surface into a kind of resonant cavity. In either case, when the newly formed black hole rings during its ring-down, some of the gravitational wave energy, instead of just radiating outward, could bounce off this quantum structure. It would be reflected back inward, only to hit the inner boundary of this cavity and bounce back out again, creating a faint, delayed copy of the original signal, an echo. Each time the wave bounces, it would lose a little energy, producing a series of successively quieter echoes following the main gravitational wave crash. The search for these echoes is like trying to hear a whisper in a hurricane. The initial gravitational wave signal from a black hole merger is incredibly powerful, but the proposed echoes would be exponentially fainter, buried deep within the noise of the detectors. A few years ago, a team of physicists analyzed the publicly available data from the LIGO Observatory's first few detections and reported a statistically significant signal consistent with such echoes. Their analysis suggested a pattern of repeating waveforms following the main event, a finding that, if true, would be nothing short of revolutionary. It would be the first direct observational evidence of physics beyond Einstein's general relativity, a glimpse of quantum gravity in action. Unsurprisingly, this claim ignited a firestorm of debate within the astrophysics community. The central challenge is one of statistical significance and data analysis. Other research groups, using different methods and more sophisticated noise models, have since reanalyzed the same data and found no compelling evidence for echoes. They argue that the initial signals identified as echoes could be explained by random noise fluctuations or subtle instrumental artifacts that are not yet fully understood. The gravitational wave detectors are marvels of engineering, but they are also incredibly complex, and characterizing every possible source of background noise is a monumental task. Skeptics point out that the echo signal is so faint that it sits right at the threshold of what the detectors can perceive, making it exceptionally difficult to distinguish a true cosmic signal from a rare statistical glitch. The debate is a perfect example of the scientific process at its most rigorous and most cautious. Extraordinary claims require extraordinary evidence, and the claim of detecting quantum gravity echoes is about as extraordinary as it gets. Proponents of the echo hypothesis continue to refine their search methods, applying them to the growing catalog of gravitational wave events detected by LIGO and Virgo. With each new merger, the statistical power increases. If echoes are real, they should appear consistently across multiple events with similar black hole masses, following a predictable pattern. The absence of such a pattern in a larger dataset would be a strong argument against their existence. What is truly at stake in this search is the fundamental architecture of a black hole. confirmation of gravitational wave echoes would shatter the classical picture of a simple, featureless event horizon. It would provide strong, indirect evidence for a physical structure outside the black hole, something that modifies the vacuum of space in its most extreme gravitational field. This could be the long-sought signature of a firewall, or it could point toward the fuzzy, quantum gravitational structure predicted by theories like loop quantum gravity. Either way, it would mean that the point of no return is not as smooth and uneventful as Einstein predicted. The echoes would be our first direct sonic map of the quantum nature of spacetime, revealing that the boundary of a black hole is a dynamic region with its own physics, rather than a silent and absolute end. The ongoing hunt for these faint reverberations is a testament to our desire to push beyond the known, to listen carefully not just for the crash of colliding black holes, but for the subtle whispers that might reveal what lies just beyond the threshold. The elegance of the no-hair theorem and the profound link between a black hole's entropy and its surface area lead us to a discovery that forever tied these gravitational giants to the science of heat and energy. In the early 1970s, the young physicist Stephen Hawking, along with Brandon Carter and James Bardeen, formulated a set of laws for black hole mechanics. To their astonishment, these laws bore an uncanny, mathematical resemblance to the classical laws of thermodynamics. The law that the area of a black hole's event horizon can never decrease, for instance, mirrored the second law of thermodynamics, which states that the total entropy of a closed system always increases. This was more than a curious analogy. It was a powerful hint that black holes were not cold, dead objects, but were somehow thermodynamic systems in their own right. Hawking initially resisted this idea, arguing that if black holes truly had a temperature, they would have to emit radiation, which seemed impossible by their very definition. But then, he performed a calculation that turned the world of theoretical physics upside down. By applying the bizarre rules of quantum mechanics to the curved spacetime right at the edge of a black hole's event horizon, Hawking made a revolutionary prediction. He showed that black holes are not completely black after all. They glow with a faint heat. This phenomenon, now known as Hawking radiation, arises from the strange behavior of the quantum vacuum. Empty space is not truly empty. It is a seething sea of virtual particle pairs constantly popping into and out of existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and paying the energy back. Normally, this process is undetectable, but place this quantum froth near the intense gravitational field of a black hole, and something extraordinary can happen. If a virtual particle pair appears right at the event horizon, the tremendous tidal gravity can rip the two particles apart before they have a chance to annihilate. One particle falls into the black hole while the other escapes into space. From the perspective of a distant observer, the black hole has just emitted a particle. To conserve energy, the particle that fell in must have negative energy relative to infinity. This negative energy particle reduces the mass of the black hole. The net result is that the black hole has lost a tiny bit of mass and has emitted a particle of radiation. This process, happening continuously all over the event horizon, gives the black hole a perfect thermal spectrum. It has a temperature, and that temperature is inversely proportional to its mass. A stellar mass black hole has a temperature of just a few billionths of a degree above absolute zero, far colder than the cosmic microwave background, meaning it absorbs more energy from the universe than it emits. But for a very small black hole, the temperature would be enormous, and the evaporation process would accelerate dramatically. This brilliant synthesis of quantum mechanics and general relativity solved one mystery while creating another, known as the trans-Planckian problem. The calculation that predicts Hawking radiation relies on treating the spacetime around the black hole as a smooth, classical background, while the quantum fields that produce the particles are treated as small perturbations on that background. This works beautifully, But when you trace the origin of the radiation back to its source, you encounter a profound puzzle. The particle that escapes to infinity, which we detect as low-energy Hawking radiation, started its life as an incredibly high-frequency wave mode. In fact, to produce the radiation we see, these modes must have had wavelengths shorter than the Planck length at the moment they were generated. The Planck length is the scale at which the classical concept of smooth spacetime is believed to break down, and quantum gravity effects must take over. It is the smallest possible meaningful unit of length. This is the trans-Planckian problem. Hawking's calculation assumes that we can trust our understanding of physics on scales where we know it must fail. It's like using the rules of fluid dynamics to describe the flow of water, but then discovering that your calculation requires you to know what individual water molecules are doing at a scale far smaller than the molecule itself. The origin of Hawking radiation seems to depend on physics in a regime where our current theories are completely silent. This suggests that the standard derivation, while giving the right answer, may be resting on a shaky foundation. The true, quantum gravitational description of the event horizon might modify the story significantly. Perhaps the radiation doesn't originate from vacuum fluctuations right at the horizon, but from quantum effects within a thin shell just outside it. Or maybe the holographic principle provides the answer, with the radiation being emitted from the quantum degrees of freedom on the horizon's surface, avoiding the trans-Planckian issue entirely. The unresolved nature of this problem is a stark reminder that Hawking's magnificent discovery, while almost certainly correct in its conclusion, points toward a deeper layer of reality that we have yet to uncover, a layer where the smooth fabric of spacetime gives way to a discrete quantum structure. Now, we venture into one of the most elegant and profound conjectures to emerge from the battlefields of theoretical physics, a concept that dares to connect two of the most bizarre phenomena in the universe. It's called the ER equals EPR conjecture, and while it sounds like a cryptic equation, its implications are truly cosmic. To understand it, we need to revisit two foundational ideas, each named for the brilliant minds that conceived them. The first is EPR, standing for Einstein, Podolsky, and Rosen. In 1935, these three physicists published a paper highlighting what they saw as a deeply unsettling feature of quantum mechanics: entanglement. They described a scenario where two particles could become linked in such a way that measuring the property of one would instantaneously determine the property of the other, no matter how far apart they were separated. Einstein famously called this spooky action at a distance, believing it pointed to an incompleteness in quantum theory, as it seemed to violate the speed of light limit for information transfer. The second part of the puzzle is ER, which stands for Einstein and Rosen. In the very same year, the same Einstein, along with Nathan Rosen, published another paper exploring the solutions to his equations of general relativity. They discovered that the mathematical description of a black hole could be extended to form a bridge connecting two distant regions of spacetime, what we now call an Einstein-Rosen bridge, or more popularly, a wormhole. For decades, these two ideas, EPR and ER, lived in separate worlds. Entanglement was a quantum mystery, a ghostly connection that defied locality. Wormholes were a relativistic fantasy, a cosmic shortcut that warped geometry. They were seen as completely unrelated consequences of two fundamentally incompatible theories. The ER equals EPR conjecture, largely championed by physicists like Leonard Susskind and Juan Maldacena, proposes a breathtaking synthesis. It suggests that these two concepts are not just analogous. They are literally two different descriptions of the same underlying reality. The spooky action at a distance of quantum entanglement is, according to this idea, physically mediated by a tiny, non-traversable wormhole. When two particles become entangled, the conjecture claims, a microscopic Einstein-Rosen bridge forms between them, weaving their separate locations into a single, connected geometric structure. In this picture, entanglement is not a mysterious, non-local force. It is a manifestation of a physical, albeit incredibly small, tunnel in the fabric of space-time. The particles are not communicating faster than light. They are, in a geometric sense, right next to each other, connected through a hidden dimension. This radical proposal offers a potential geometric foundation for quantum mechanics itself. It provides a visual, almost tangible, explanation for why entangled particles behave as a single system. They are part of a common geometric object. Furthermore, this idea opens a fascinating path toward resolving the infamous firewall paradox we discussed earlier. Recall the terrible choice. Either information is lost, violating quantum mechanics, or a deadly firewall exists, violating general relativity. The ER equals EPR conjecture suggests a third way. If the Hawking radiation particles leaving an evaporating black hole remain entangled with the black hole's interior, then, according to this conjecture, they must be connected by microscopic wormholes. These wormholes would create a kind of quantum backdoor, a direct geometric link that allows information to escape from inside the black hole to the outside radiation without ever having to pass through the event horizon. The information isn't radiated away randomly. It is transmitted through these hidden space-time tunnels, preserving the laws of quantum mechanics without the need for a violent, paradox-creating firewall. From the outside, the black hole evaporates, releasing information. From the inside, the geometry remains smooth, allowing an astronaut to fall in peacefully. The paradox is resolved by recognizing that the interior of the black hole and the distant radiation are not separate entities. They are woven together by the quantum threads of wormholes. Of course, this is a highly speculative idea, and it comes with its own set of profound challenges. The wormholes described by ER equals EPR are not the traversable wormholes of science fiction. They are often described as non-traversable or ghost wormholes, meaning that while they provide a geometric connection for quantum information, they are far too small and unstable for any matter or signal to pass through. They are like the quantum foam of space-time, but with a specific, organized structure linking entangled particles. Another major hurdle is scale. The wormholes connecting elementary particles would be unfathomably tiny, operating at the Planck scale, far beyond any possibility of direct observation with current technology. For now, ER equals EPR remains a powerful and inspiring framework, a piece of mathematical poetry that hints at a deeper, geometric unity underlying all of physics. It represents a bold step toward the ultimate goal of unifying general relativity and quantum mechanics, suggesting that the key to solving our greatest paradoxes may lie in understanding that the quantum weirdness of entanglement and the gravitational warping of wormholes are, in the final analysis, one and the same. Yet another radical solution to the information paradox emerges not from modifying the rules of quantum mechanics or relativity, but from reimagining the very essence of a black hole from the ground up. This is the fuzzball proposal, a fascinating concept born from the intricate mathematics of string theory. If the idea of a smooth event horizon and a crushing singularity lies at the heart of our paradoxes, then the fuzzball theory offers a simple yet profound answer: they don't exist. In this view, what we call a black hole is not a vacuum solution with a point of infinite density at its core. Instead, it is a gigantic, tangled ball of vibrating strings, a quantum mechanical object that has a definite, albeit highly complex, structure all the way to its center. The name itself is wonderfully descriptive. A fuzzy ball, a region of space filled with a vibrant, chaotic soup of the fundamental strings that string theory posits as the building blocks of reality. To understand how this solves the paradox, we need to revisit the classical picture. The traditional black hole is mostly empty space, with all the mass collapsed into an infinitely small point. The event horizon is just a gravitational boundary in that empty space, a point of no return with no physical substance. The fuzzball proposal turns this inside out. It suggests that the mass of the black hole never actually collapses to a singularity. The immense gravitational pull causes the matter to transform into a vast, intricate network of strings and higher-dimensional membranes, known as branes. These strings and branes swell to fill the entire volume that would have been the black hole's interior, right up to what would have been the event horizon. There is no sharp boundary, no empty space inside, and no singularity. The black hole, in essence, is a star, but a star made of the weirdest stuff imaginable, a quantum fuzz. This reorganization of the black hole's anatomy has dramatic consequences for the information paradox. In the classical view, information vanishes behind the horizon and is lost when it hits the singularity. In the fuzzball picture, there is no inside to fall into. An object approaching the fuzzball would interact with its outermost layers, which are made of the same kind of quantum constituents as anything else in the universe. There is no smooth passage across an event horizon because the horizon is replaced by the actual, physical surface of the fuzzball. When matter falls into a fuzzball, it simply merges with the fuzz, adding its energy and, crucially, its information to the intricate quantum state of the entire object. The information is never lost. It is scrambled and distributed throughout the fuzzball's complex structure, much like the information in a burning book is scrambled into the heat, light, and smoke. It becomes incredibly difficult to retrieve, but it is not gone from the universe. This provides a natural and elegant explanation for black hole entropy. Recall that a black hole's entropy is proportional to the area of its event horizon. In the fuzzball paradigm, the entropy is no longer a mysterious property of a boundary. It is the straightforward result of the astronomical number of ways the strings and branes within the fuzzball can be arranged or vibrated. The surface area is simply a measure of the size of this complex quantum system. The information capacity is huge because the fuzzball itself is a vast repository of quantum states. Hawking radiation in this model is not a mysterious quantum trick happening at an empty horizon. Instead, it is the thermal radiation emitted by this hot, complicated object, a fuzzball, just as any hot body radiates. Because the radiation is emitted from a body with a definite quantum structure, it can carry away information about that structure in a perfectly natural way, resolving the paradox without the need for firewalls or other drastic measures. Of course, such a radical idea is not without its challenges. The primary hurdle is that the mathematics of fuzzballs are formidably complex, and deriving the properties of a large, macroscopic black hole from first principles in string theory remains an immense task. Furthermore, the proposal suggests that for every possible black hole characterized by its mass, charge, and spin, there is a corresponding unique fuzzball configuration. While this is precisely what is needed to encode the information, verifying this through calculation for realistic black holes is currently beyond our reach. There is also the question of what an observer falling into a fuzzball would experience. Without a smooth event horizon, the free-falling astronaut would not have an uneventful passage. They would collide with the fuzzball's surface. However, proponents argue that at the moment of impact, the incoming matter would already be composed of strings, and the interaction would be a complex merging process rather than a violent crash. The fuzzball proposal remains a highly promising but still developing frontier in theoretical physics, a testament to the power of string theory to offer concrete, if mind-bending, solutions to the universe's most stubborn mysteries. From the dance of binary black holes to the faint whispers of possible echoes, we see how these objects interact on a local scale, but their influence extends to the very largest structures in the cosmos, shaping the destinies of entire galaxies. This brings us to a profound and symbiotic mystery: the intricate co-evolution of supermassive black holes and the galaxies they call home. For a long time, black holes were seen as cosmic vacuum cleaners, passive endpoints for matter. But a series of stunning discoveries revealed that they are anything but passive. They are active, powerful engines that can either nurture or strangle the galaxy around them, and the nature of this relationship is one of the great puzzles of modern cosmology. The first major clue came when astronomers noticed a surprising correlation that seemed too precise to be a coincidence. They found that the mass of a galaxy's central supermassive black hole is intimately linked to the properties of the galaxy itself, specifically with the velocity dispersion of the stars in the galaxy's central bulge. That is, how fast those stars are moving around. The more massive the black hole, the larger and faster moving the stellar bulge. This correlation, known as the M-sigma relation, is remarkably tight. It suggests that the growth of the black hole and the growth of the galaxy are not independent processes. They are somehow in lockstep, communicating with each other across billions of years. A black hole millions of times the mass of our Sun doesn't end up in a small, tranquil galaxy. It resides in a giant, with a correspondingly giant stellar population. This cosmic scaling law is a clear signal that the fates of the black hole and its host galaxy are deeply entwined, but the mechanism for this coordination is hotly debated. The leading theory to explain this partnership is known as black hole feedback. Imagine a supermassive black hole at the center of a galaxy, actively feeding on gas. As we've seen, this process can generate incredible energy, not just in the form of radiation from the hot accretion disk, but also through the powerful relativistic jets that blast outward from its poles. This feedback is a classic case of a cosmic thermostat. When the black hole feeds too greedily, the resulting outbursts of energy and radiation heat up the surrounding gas in the galaxy. This heated gas becomes too energetic to collapse under its own gravity to form new stars. In this way, the black hole effectively regulates star formation, preventing the galaxy from growing too large too quickly. It can even blow huge bubbles of hot gas out of the galaxy entirely, starving it of the raw material needed for future stellar generations. This is negative feedback, a self-regulating mechanism where the black hole's own growth prevents the galaxy from overfeeding it, creating the observed correlation between black hole mass and galactic properties. But is the black hole the master regulator, or merely a symptom of the galaxy's growth? This is the core of the active debate. An alternative viewpoint suggests that the correlation arises not from the black hole's feedback, but from the larger-scale dynamics of the galaxy itself. In this scenario, the primary driver is the inflow of gas from the galactic halo or from mergers with other galaxies. Vast reservoirs of cold gas flow inward, fueling both a burst of star formation in the galactic center and providing a feast for the central black hole. In this view, the black hole and the galaxy grow in tandem because they are both being fed from the same cosmic pantry. The black hole's feedback might be real, but it's a secondary effect, a spectacular sideshow to the main event of galactic evolution driven by gravity and gas dynamics. The correlation exists because both the black hole's growth and the bulge's growth are consequences of the same underlying process. The truth likely lies in a complex, cyclical dance between these two ideas. It may be a case of cosmic cause and effect blurring together over billions of years. A major merger of galaxies funnels a huge amount of gas to the center, simultaneously triggering a starburst and activating the black hole as a quasar. The black hole then responds with a powerful feedback phase, quenching the very star formation that helped fuel it. This cycle of feeding and feedback, of construction and destruction, could naturally lead to the observed tight correlation. The challenge for astronomers is to observe this process in action across cosmic time. By looking at distant galaxies, we see back in time, witnessing younger galaxies and their active black holes. Observations show that in the early universe, when galaxies were gas-rich and forming stars furiously, their black holes were also more active. As galaxies aged and their gas reservoirs were depleted or heated, both star formation and black hole activity declined in sync, leaving behind the quiet, mature systems we see today like our own Milky Way. Unraveling this mystery is crucial because it tells us why galaxies look the way they do. The giant elliptical galaxies, devoid of much young gas and new stars, may be the products of powerful feedback events in their past. Spiral galaxies like our own, with more modest central black holes, may have had a gentler evolutionary history. The co-evolution of black holes and galaxies is therefore not just an academic curiosity. It is the story of how the universe transitions from a chaotic, star-forming youth to the more orderly, structured cosmos we see today. It reveals that the most massive objects in the universe are not isolated monsters, but integral components of their galactic ecosystems, wielding a power that can dictate the very life cycle of stars and shape the grand architecture of the cosmos itself. Returning to the concept of these ancient cosmic fossils, the mystery of primordial black holes deepens considerably when we consider the specific conditions required for their birth. Unlike stellar black holes that form from the dramatic deaths of massive stars, primordial black holes are thought to be a direct consequence of the universe's violent infancy. The leading theory posits that they were forged in the first fleeting fraction of a second after the Big Bang, during a period of exponential expansion known as inflation. During this epoch, tiny quantum fluctuations in the density of the primordial energy field were stretched to macroscopic sizes. In most regions, these density variations were minor, but in rare pockets where the fluctuation was particularly intense, the gravitational pull would have been so strong that the region would collapse directly upon itself, bypassing the need for a star and forming a black hole almost instantaneously. The mass of these primordial black holes would be determined by the size of the horizon at the moment of their collapse, meaning they could have formed with a stunning range of masses, from as light as a miniature speck smaller than an atom to colossal entities weighing thousands of suns. This versatility is both the strength and the challenge of the theory. If primordial black holes can form across such a vast mass spectrum, they could potentially account for all, or at least a significant portion, of the dark matter that holds galaxies together. However, decades of meticulous astronomical observation have acted like a series of sieves, progressively filtering out which mass ranges could realistically constitute the dark matter we infer. The most powerful constraint comes from gravitational microlensing surveys. The principle is straightforward. If a vast population of planet-sized or asteroid-mass primordial black holes were drifting through the halo of our galaxy, they would occasionally pass directly in front of a distant star. Their gravity would bend the starlight, acting as a gravitational lens and causing the star to temporarily brighten. Projects like the Optical Gravitational Lensing Experiment, or OGLE, and the Massive Compact Halo Object, or MACHO, survey monitored millions of stars for years. Their results were decisive. There simply are not enough of these microlensing events to allow for primordial black holes in the mass range of a large asteroid to about 100 times the mass of our Sun to be the primary component of dark matter. The window for these objects was effectively slammed shut. But the cosmos, in its infinite complexity, has left a few tantalizing cracks in the door. Two specific mass windows remain intriguingly open. The first is for extraordinarily low-mass black holes. If a primordial black hole formed with a mass less than that of a small mountain, roughly 1 billion metric tons, the mathematics of Hawking radiation dictate that it would have completely evaporated by now, ending its life in a final, minuscule burst of gamma rays. The non-detection of a background of such explosions suggests they are not common, but it doesn't entirely rule out their past existence. The second, and far more compelling, window is at the opposite end of the scale. For intermediate mass primordial black holes, ranging from about 1,000 to 100,000 solar masses. These objects would be too massive and rare to produce frequent microlensing events that our current surveys could detect. Yet if they were numerous enough, their collective gravity could still account for the dark matter gravitational pull we observe in galactic halos. Furthermore, they would be the perfect ready-made seeds for the supermassive black holes we see in the early universe, solving the mystery of how those giants grew so quickly. The hunt for evidence is now entering a new, revolutionary phase with the advent of gravitational wave astronomy. While ground-based detectors like LIGO and Virgo are superb at finding stellar mass black hole mergers, they are not sensitive to the low-frequency ripples produced by the inspiral of these intermediate mass behemoths. That is the primary mission of future space-based observatories, most notably the Laser Interferometer Space Antenna, or LISA. Scheduled for launch in the next decade, LISA will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, forming a gravitational wave observatory of unprecedented scale. It will be exquisitely tuned to hear the deep, rumbling hum of merging black holes in the intermediate mass range. If a significant population of primordial black holes in this window exists, LISA should detect their cosmic mergers. The signature would be unmistakable: a statistical distribution of mergers occurring not in the crowded environments of galaxies, but out in the relative emptiness of intergalactic space, where these ancient relics would be expected to wander. A detection like this would be more than just confirming a type of black hole. It would fundamentally reshape our understanding of dark matter, suggesting that the invisible glue of the cosmos is not a sea of exotic particles, but a sky full of ancient, shadowy giants born from the first moments of time. Looking trillions upon trillions of years into the future, we find a universe that has grown cold and dark. Stars have long since burned out, galaxies have evaporated, and the cosmos is dominated by the fading embers of stellar remnants, white dwarfs and neutron stars slowly cooling toward absolute zero. But even these will not last forever. Over timescales so vast they dwarf the current age of the universe, a process of proton decay, if it occurs, will eventually dissolve all ordinary matter into a thin soup of subatomic particles and radiation. In this bleak, distant era, the last significant structures remaining will be black holes. Yet, as Stephen Hawking taught us, even these gravitational titans are not eternal. They too have a fate, and it is governed by the faint, quantum whisper of Hawking radiation. But what exactly happens in the final moments of a black hole's life is a mystery that forces us to confront the ultimate limits of our physical laws. As a black hole radiates away its mass through Hawking radiation, a fascinating and counterintuitive thing happens: it heats up. The temperature of a black hole is inversely proportional to its mass. A giant, supermassive black hole is incredibly cold, but as it loses mass, it shrinks and its temperature rises. This creates a runaway process. The hotter it gets, the faster it radiates energy. The faster it radiates, the more mass it loses, causing it to heat up even more rapidly. In its final stages, a black hole that began with the mass of a star would be emitting energy not as a faint trickle, but as a spectacular outburst of high-energy particles and radiation. For the last second of its existence, this microscopic black hole would briefly shine with the power of millions of hydrogen bombs, a final, brilliant flash in the darkness before it presumably vanishes. The classical prediction from Hawking's original calculation is that this process continues unabated until the black hole's mass reaches zero, disappearing from the universe without a trace. But this conclusion, known as the complete evaporation scenario, slams headfirst into the fundamental principles of quantum mechanics, resurrecting the information paradox in its most extreme form. If the black hole vanishes completely, taking the singularity with it, then what happens to all the information about every star, planet, and book that ever fell in? Quantum mechanics insists that information cannot be destroyed. The information must be encoded in the Hawking radiation that is released during the evaporation process. However, Hawking's original work suggested this radiation is purely thermal, like the glow from a hot stove. containing no information about the black hole's internal history. If the radiation is random heat, and the black hole vanishes, then the information is irretrievably lost. This would mean that the universe's ultimate ledger has pages ripped out, violating a cornerstone of physics. The complete evaporation scenario presents a universe with a fundamental case of cosmic amnesia. To rescue the principle of information conservation, many physicists are drawn to a radically different possibility: the black hole remnant. This theory proposes that the evaporation process does not go all the way to zero. Instead, it halts when the black hole shrinks to a microscopic size, perhaps near the Planck scale, the smallest possible unit of length. At this point, the intense quantum gravitational effects that we currently don't understand would become dominant, preventing further collapse and stopping the evaporation. The result would be a stable, permanent relic, a tiny, massive particle containing within its quantum structure all the information that the black hole ever absorbed. This remnant would be a fossil, a time capsule holding the entire history of the black hole's diet. The information is saved because it is not released. It is permanently locked away in this indestructible, final state. Each of these fates carries mind-boggling implications for the far future of the cosmos. If black holes evaporate completely, the late universe would be a truly barren place. After the last black hole flashes out of existence, the cosmos would be left with only a dilute, cold sea of particles and low-energy radiation, drifting forever toward maximum entropy, a state known as the heat death. The history of stars, galaxies, and life would be erased not just from active memory, but from the very fabric of reality, with no remaining structures to encode it. It is the ultimate quiet ending. If, however, black hole remnants are real, the distant universe would be littered with these invisible, information-rich specks. They would be the sole survivors of the age of stars, drifting through the eternal darkness. Their existence would mean that the universe's history is never truly lost, merely locked in a vault that can never be opened. But this scenario creates its own set of profound puzzles. What would such a remnant be made of? How could an object with potentially immense information content have no other detectable properties? Furthermore, the number of possible internal states for a remnant that has swallowed entire galaxies would be astronomically large, leading to a concept known as infinite entropy. Some physicists argue that this is just as problematic as information loss, as it could lead to paradoxical probabilities in particle interactions. The resolution of this mystery lies squarely in the domain of a theory of quantum gravity. The final scream of an evaporating black hole is a regime where energies are unimaginably high, and spacetime itself is undergoing a violent phase transition. Only a theory that successfully unites general relativity with quantum mechanics can describe what truly occurs. Perhaps the evaporation process subtly encodes the information into the Hawking radiation in a way we cannot yet calculate, a complex scrambling that preserves the quantum laws. Or perhaps the black hole does transform into a stable remnant, a new form of matter that represents the ultimate endpoint of gravitational collapse. Determining the final fate of a black hole is not just about understanding the death of a cosmic object. It is about answering whether the universe ultimately respects its own rules, and whether anything, even a black hole, can truly erase the past. We have explored black holes from the scale of cosmic collisions down to their final evaporation, but to truly grasp the paradoxes they present, we must zoom in to the very edge of reality, to the microscopic quantum dance taking place at the event horizon itself. This is not the domain of planets and stars, but of virtual particles and quantum fields, where the smooth predictions of general relativity are challenged by the inherent uncertainty of the quantum world. The event horizon, classically a perfectly sharp and definite boundary, begins to look blurred and unstable when we apply the magnifying glass of quantum mechanics, leading to phenomena even stranger than Hawking radiation. To set the stage, we need to appreciate the nature of the quantum vacuum. What we call empty space is anything but. Due to the Heisenberg uncertainty principle, space is a seething foam of virtual particle pairs constantly flickering in and out of existence. These pairs, typically a particle and its antiparticle, borrow energy from the vacuum for an incredibly brief moment before annihilating each other and repaying the debt, leaving no trace. This process is happening everywhere all the time. Now, bring a black hole's immense gravitational field into the picture. The event horizon creates a drastic division in spacetime. What happens if one of these virtual pairs appears right at the precipice? If the two particles are created such that one ends up just outside the horizon and its partner just inside, their brief marriage is torn apart by the fundamental nature of the black hole. The particle outside can escape to infinity, becoming a real particle of Hawking radiation, while the particle inside falls inward, carrying negative energy and causing the black hole to lose mass. This is the standard, though simplified, picture of how black holes evaporate. But this description relies on a crucial assumption, that the event horizon is a static, perfectly defined surface in a classical spacetime. The quantum world suggests this might be an oversimplification. A more precise, though mathematically complex, description involves quantum fields. Instead of thinking about particles, we consider fields, like the electromagnetic field, that permeate all of space. Near the event horizon, the intense gravity dramatically alters the behavior of these fields. From the perspective of an observer far from the black hole, who is stationary relative to it, the vacuum near the horizon doesn't look empty at all. It appears to be filled with a thermal bath of radiation. This is the Hawking radiation we've discussed. However, an observer falling freely with the flow of space into the black hole would perceive the vacuum near the horizon as truly empty. This stark difference in perception is a classic example of relativity. What one observer sees as a seething heat bath, another sees as a cold void. This strange relativity of particle detection leads us to a fascinating parallel phenomenon known as UNRA radiation. Imagine an astronaut floating in the complete emptiness of interstellar space, far from any gravitational fields. They would measure the temperature of the vacuum as absolute zero. It's empty. But if that same astronaut suddenly fires their rockets and accelerates at a constant rate, their perspective shifts dramatically. From their accelerating frame of reference, they would find themselves immersed in a warm bath of thermal radiation. The vacuum would no longer feel empty. It would have a temperature proportional to their acceleration. This is UNRA radiation. It's not radiation coming from anywhere. It's a quantum effect where the accelerated motion of the detector through the vacuum causes it to perceive virtual particles as real. The event horizon of a black hole acts in a similar way for a stationary outside observer. Because the gravitational pull is so strong at the horizon, staying stationary there would require an acceleration equal to the speed of light squared divided by the Schwarzschild radius, an acceleration that approaches infinity as you get closer. This immense effective acceleration is why the outside observer sees the hot Hawking radiation. UNRA radiation and Hawking radiation are deeply connected, two sides of the same coin showing how motion and gravity can tease real particles out of the quantum vacuum. This quantum perspective forces us to question the very nature of the event horizon. Is it the sharp, mathematical boundary that general relativity describes? Or is it a fuzzy, quantum mechanical region? The process of Hawking radiation itself suggests an instability. The emission of radiation causes the black hole to lose mass, which makes the event horizon shrink slightly. But this is a continuous process. The horizon is constantly fluctuating in size and shape at the quantum level. It's not a static razor's edge, but a dynamic and blurry membrane. Furthermore, the energy required to create a Hawking radiation particle comes from the black hole's mass, which is tied to the gravitational field. This means the gravitational field itself must be undergoing quantum fluctuations. At scales approaching the Planck length, the fabric of spacetime is expected to become foamy and discrete. This quantum foam would likely make the precise location of the event horizon fundamentally uncertain. It wouldn't be a definite point of no return, but a probabilistic region where the chance of escape drops from possible to impossible over a tiny, but finite, width. It becomes a quantum fog rather than a classical wall. This concept of a fuzzy horizon has profound implications for the firewall paradox and the fate of infalling matter. If the horizon is not a perfectly sharp surface, then the argument for a sudden, violent firewall might be softened. The transition from the outside universe to the interior of the black hole could be a gradual one, a smooth fading of possibilities rather than an abrupt cliff. Some theories suggest that the horizon is replaced by a quantum atmosphere, a region extending slightly outside the classical horizon where the Hawking radiation is actually generated. In this view, an astronaut falling in might not experience a sudden inferno at a precise point, but would instead be gradually heated by the increasing temperature of this quantum atmosphere as they approached. The question of whether information is lost or saved might hinge on the detailed quantum structure of this fuzzy boundary. Is information smeared across this quantum region, or does it pass through relatively unscathed? The event horizon, once thought to be the simplest part of a black hole, is now seen as a quantum laboratory where the fate of information and the nature of spacetime are decided. Its apparent sharpness is an illusion of large-scale physics, masking a turbulent quantum reality that we are only beginning to fathom. While we often picture black holes as purely gravitational monsters, their most spectacular displays of power are actually governed by an invisible force, magnetism. This brings us to a mystery that lies not at the singularity, but in the frenzied chaos just outside the event horizon. We've seen how relativistic jets, those million light-year-long blowtorches, require an incredible engine, and the prime suspect is the black hole's magnetic field. But how does a black hole, an object defined by its ability to trap everything including light, generate and sustain such powerful magnetic fields? The answer is not etched on the event horizon but is woven into the dynamics of its swirling meal ticket, the accretion disk. The process is a masterpiece of cosmic engineering. As gas from a companion star or a surrounding cloud spirals inward, it forms a hot, ionized plasma, a sea of charged particles like electrons and protons. This plasma is not moving through a vacuum. It carries with it magnetic field lines, frozen into the material like threads in a flowing river. As the disk rotates, differential rotation sets in. The inner parts orbit much faster than the outer parts. This shearing motion stretches, twists, and amplifies these magnetic field lines, winding them up like a twisted rubber band. This mechanism, known as the magnetorotational instability, is thought to be the primary dynamo that transforms a weak, initial seed field into a powerful, organized structure. The magnetic field becomes tightly coiled, creating a powerful slingshot that can channel and accelerate material away from the black hole's poles. In some models, the black hole's own spin acts as a central rotor. As the black hole spins, it drags the very fabric of spacetime around with it in a region called the ergosphere. If magnetic field lines are anchored in this whirling spacetime, the rotating black hole can act like a gigantic battery, transferring its immense rotational energy directly to the magnetic field, powering the jet in a process known as the Blandford-Zenagic mechanism. Yet, a major puzzle remains. Where does the initial seed magnetic field come from? Is it imported from the interstellar medium, dragged in with the infalling gas? Or can it be generated locally within the turbulent plasma of the accretion disk itself through the complex motions of charged particles? Furthermore, the sheer strength of these fields is staggering. Near the event horizon of a supermassive black hole, magnetic fields can be billions of times stronger than Earth's magnetic field. creating pressures that can rival the black hole's own gravitational pull. How such intense fields are confined and stabilized without immediately dissipating or tearing themselves apart is an active area of research, involving complex magnetohydrodynamic simulations that model the behavior of this hot, magnetized soup. This leads to another perplexing aspect of the mystery: the dramatic inconsistency from one black hole to another. Why do some black holes, like the one at the heart of the galaxy M87, produce jets that punch across galactic distances, while others, like Sagittarius, a star at the center of our own Milky Way, are relatively quiet, with only faint, occasional outbursts? The difference likely lies in a delicate balance between three key factors: the black hole's spin, the rate at which it is feeding, and the configuration of its magnetic field. A rapidly spinning black hole provides a vast reservoir of rotational energy that can be tapped by the magnetic field to launch a jet. However, a fast spin alone is not enough. The black hole also needs a steady supply of gas to maintain the accretion disk and the magnetic dynamo within it. If the feeding rate is too low, the disk may become faint and inefficient, unable to sustain the necessary magnetic structures. This seems to be the case for our galactic center black hole, which is on a relative diet. Conversely, a black hole that is feeding too greedily might create a disk that is too dense and optically thick, which could actually trap the magnetic field and prevent the formation of a clean, collimated jet. The most powerful jets may require a Goldilocks zone of accretion, not too little, not too much, but just right. The structure of the magnetic field is equally critical. A simple, disorganized field won't create a focused jet. It will just create turbulence. Observations suggest that for a jet to form, the magnetic field needs to have a large-scale, ordered poloidal structure, meaning the field lines run in a coherent loop from the poles of the black hole down through the disk. This organized geometry acts as a nozzle, collimating the ejected plasma into a tight beam. How such an ordered field emerges from the inherent chaos of the accretion flow is a mystery in itself. It may be that the flow of gas itself helps to organize the field, or that the field, once strong enough, begins to dictate the flow of the gas in a powerful feedback loop. Understanding this magnetic field mystery is not just about explaining spectacular cosmic fireworks. It's about comprehending one of the most efficient energy conversion processes in the universe. These magnetic fields are the invisible architects that allow black holes to transform gravitational energy into radiant light and kinetic energy on a scale that can shape the evolution of entire galaxies, proving that even the darkest objects in the cosmos are governed by forces of incredible power and subtlety. We have explored black holes as cosmic endpoints, but what if their strange physics also holds the key to understanding the very beginning of everything? This idea takes us to one of the most profound and elegant proposals in modern cosmology, a concept that attempts to describe the ultimate origin of the universe, and in doing so, finds a surprising parallel with the nature of a black hole singularity. It's known as the no-boundary proposal, developed by Stephen Hawking and James Hartle in the 1980s, and it seeks to answer a question that has puzzled philosophers and scientists for millennia. What was there before the Big Bang? The standard Big Bang model presents a familiar but deeply troubling image. It describes a universe exploding from a state of infinite density and temperature, a primordial singularity. This is a point where all the laws of physics break down, a definitive beginning to both space and time. But this raises an immediate conceptual problem. If time itself began at the Big Bang, then the phrase "before the Big Bang" is meaningless. There is no before, just as there is no south of the South Pole. The universe simply pops into existence from a state of mathematical nonsense. Hawking and Hartle found this unsatisfying. They asked a more refined question. Could the universe have a beginning without actually having a boundary, a singular edge in time? Their ingenious proposal uses a mathematical technique called Wick rotation, which essentially treats time as if it were a dimension of space under certain conditions. In this framework, the history of the universe is not like a straight line starting at a point. Instead, it is more like the surface of a sphere, such as the Earth. Consider asking, what is north of the North Pole? The question doesn't make sense because the North Pole is a boundary on a flat map, but not on the globe itself. The surface of the Earth has no edge. You can travel forever without falling off. Similarly, Hawking and Hartle propose that if we consider the entire four-dimensional fabric of spacetime, 3 dimensions of space and 1 of time, it could be finite in extent yet have no boundary or edge. In this picture, the Big Bang is not a violent explosion from a singularity, but a smooth, rounded-off event like the South Pole on our globe. Time, as we experience it, emerges from this timeless geometry. There is no moment of creation because there is no time for a creator to act in. The universe just is, in a self-contained, complete geometry. This is where the connection to black holes becomes startlingly clear. The no-boundary proposal describes a universe that begins in a state of extreme, but not infinite, curvature. The initial moments are a hot, dense, and incredibly smooth quantum foam. Now, consider the journey of an object falling into a black hole. As it approaches the singularity, according to classical general relativity, the curvature of spacetime becomes infinite, and time, from the perspective of the outside universe, appears to stop for the falling object. The interior of a black hole, particularly as described in the complex mathematics of a rotating Kerr black hole, is a region where the roles of space and time can become blurred or even swapped. Some physicists have speculated that the conditions in the very early universe, as described by the no-boundary proposal, might bear a remarkable resemblance to the interior geometry of a black hole. Both are regions where classical notions of time break down and where quantum gravity must reign supreme. It's a mesmerizing possibility that the birth of our entire cosmos could be analogous to the formation of a singularity within a black hole, but with one crucial difference. The no-boundary proposal smooths out the infinity, replacing a sharp, lawless point with a rounded, self-consistent geometry. This line of thought leads to an even more speculative and grand idea, that our universe itself could have been born from a black hole in a larger, pre-existing meta-universe. In this scenario, the collapse of a massive star in another cosmos doesn't end in a singularity, but rather in a bounce, facilitated by quantum gravity effects, which then erupts as a new, expanding universe. The event horizon of the parent black hole would then become the cosmological horizon of our newborn universe, the point beyond which we can never see. This would elegantly explain why our universe appears so finely tuned for existence. Only those black holes that give rise to stable, expanding universes would contain observers to ponder their origin. While this remains a highly speculative hypothesis, it illustrates how the physics of black holes and the physics of the cosmos's origin are becoming deeply intertwined. The no-boundary proposal doesn't just offer a vision of a beginning without a boundary. It suggests that the ultimate fate of matter in a black hole and the ultimate origin of our reality might be two sides of the same cosmic coin, forcing us to see these gravitational anomalies not as endpoints, but as potential gateways to creation itself. The relentless forward march of time, the feeling that yesterday is gone and tomorrow is yet to come, is one of the most fundamental experiences of our existence. We call this the arrow of time, and it points inexorably from the past toward the future. It's why we remember yesterday but not tomorrow, why an ice cube melts in a warm room but never spontaneously refreezes, and why we can't unscramble an egg. At its heart, this arrow is driven by the second law of thermodynamics, the universal tendency for entropy or disorder to always increase. A messy room gets messier, not cleaner, unless energy is expended to tidy it up. Now bring a black hole into this picture, and the plot thickens in a profound way. We've already seen that a black hole possesses an immense amount of entropy, proportional to the area of its event horizon. When something falls into a black hole, the total entropy of the universe increases dramatically as the black hole's horizon area grows. In a very real sense, a black hole is the ultimate expression of the arrow of time in our cosmos. It's a one-way street that not even light can reverse, a cosmic manifestation of irreversibility. The formation and growth of a black hole is a process that screams the direction of time, locking entropy away behind a curtain from which there is no return. This connection leads to a fascinating and deeply speculative idea about the origin of time's arrow itself. Why does the universe have a preferred direction of time? The fundamental laws of physics, for the most part, are time-symmetric. The equations of motion work just as well if time runs backward as they do forward. So why does our lived experience show such a strong bias? One compelling proposal is that the arrow of time is a cosmological phenomenon set by the initial conditions of the Big Bang. The early universe was in a state of incredibly low entropy, an exceptionally ordered and smooth configuration. Since then, the universe has been evolving toward states of higher and higher entropy, and this grand increase is what we experience as the flow of time. Black holes, as the objects with the highest possible entropy density in the universe, are the ultimate endpoints of this cosmic trend. They are the sinks toward which disorder flows, the ultimate manifestations of the universe's journey from its ordered beginning toward a future of maximum disorder. In this view, the relentless growth of black holes over cosmic history isn't just a consequence of the arrow of time. It is a primary driver of it, constantly pulling the universe toward higher entropy states. But this raises a terrifying and mind-bending question. What happens to the arrow of time inside a black hole? We've discussed how, within the event horizon, all paths lead to the singularity. The direction toward the center ceases to be a direction in space and becomes your inevitable future. From the perspective of someone falling in, does time continue to flow forward toward the singularity? Or does the complete breakdown of physics at the singularity represent a point where the very concept of time ceases to have meaning? Some interpretations suggest that the interior of a black hole is a region where the cosmological arrow of time we experience on the outside might be reversed or profoundly altered. If the outside universe is evolving toward higher entropy, perhaps the interior is a domain where the rules are flipped. It's a thought that challenges the core of our understanding of causality, the principle that cause must always precede effect. Imagine crossing the event horizon. According to classical general relativity, you would still have a future, a very short and terminal one culminating at the singularity. But if the singularity is a point where time itself ends, then, from your perspective, is your personal future being rapidly used up? Does time speed up as you approach the end of the line? The equations suggest that your journey from the horizon to the singularity takes a finite amount of time on your own clock. During that fall, the singularity is not just a place, but a moment in your future. This creates a bizarre situation where the entire history of the universe outside the black hole, which could last for trillions of years, is happening in what, to you, is a matter of seconds. You are, in a sense, falling into the future of the external cosmos at an accelerated rate, while your own personal timeline is rushing toward its conclusion. The singularity, then, might not be just a point of infinite density, but the literal end of time for anything that crosses the horizon. In this nightmarish landscape, the reliable forward march of time that we depend on could become twisted and compressed, leading to a state where the ordinary sequence of cause and effect is lost in the gravitational chaos, leaving us with a profound mystery about the ultimate fate of time itself in the universe's most extreme environments. That first historic image of the glowing ring around the abyss at the heart of Messier 87 was not an ending, it was a beginning. It was the equivalent of Galileo first pointing his telescope at Jupiter and seeing its moons. A blurry, pixelated glimpse that confirmed we were looking in the right direction, but which immediately begged for a sharper, more detailed view. The next great leap in our observational quest is already underway, pushing the boundaries of technology to transform that single, static snapshot into a dynamic movie of spacetime itself, testing Einstein's theory in conditions of gravity so extreme they were once thought to be beyond our reach. The challenge is monumental, and it stems from the fundamental nature of how the Event Horizon Telescope works. It's not a single dish but a global network of radio observatories, from the high deserts of Chile to the volcanic peaks of Hawaii, all synchronized by atomic clocks to act as one planet-sized virtual telescope. The resolution, or sharpness, of any telescope is determined by its diameter. By combining signals from telescopes spread across the Earth, the EHT achieves an effective diameter equal to the size of our planet, allowing it to resolve details as fine as the event horizon of a supermassive black hole millions of light-years away. But that first image was like seeing a coin on the surface of the moon, an incredible feat, but one that used only a fraction of the potential data. Large gaps remained in the virtual dish, like a camera sensor with many dead pixels. Filling in those gaps requires more telescopes in more locations, especially in critical spots like Africa and South America, to create a more complete picture of the incoming radio waves. This global effort is driving the development of the next-generation Event Horizon Telescope. Plans include placing new radio dishes in geographically strategic locations and, even more ambitiously, launching radio telescopes into orbit. A space-based component would break the earthly limit on size, creating a virtual telescope with a diameter not of thousands of kilometers, but of hundreds of thousands. This would increase the resolution by orders of magnitude, sharpening the image from a few blurry pixels to a detailed portrait where subtle features become visible. The primary target for this increased scrutiny is a delicate structure predicted by general relativity, but not yet clearly resolved: the photon ring. This is not the bright ring of hot gas we see in the first image, but a series of incredibly sharp, nested rings of light lying just inside it. These rings are formed by photons that have orbited the black hole multiple times, skimming perilously close to the event horizon before escaping to reach our telescopes. The innermost photon ring is essentially a direct map of the black hole's spacetime geometry, a perfect circle whose size and shape are exquisitely sensitive to the black hole's mass and spin. Measuring this ring with precision would provide one of the most stringent tests of general relativity ever conducted. Any deviation from the perfect circle predicted by Einstein would send shockwaves through the world of physics, potentially revealing the fingerprints of new gravitational physics or the influence of exotic matter. Beyond a sharper still image, the ultimate goal is to create a video, to observe the event horizon in motion. The accretion disk of superheated gas swirling around a black hole is not a serene, steady-state structure. It is a violent, turbulent maelstrom. Blobs of plasma, bright magnetic flares, and shock waves should constantly dance across the face of the black hole's shadow, causing the ring of light to flicker, warp, and brighten in specific patterns over time. Capturing this cosmic film would be revolutionary. It would allow us to study the dynamics of matter under the influence of the strongest gravity in the universe, watching as it is accelerated to near light speeds and funneled toward its doom. We could directly observe the flow of energy and angular momentum, understanding how black holes power their relativistic jets and influence their galactic environments. For the black hole at the center of our own Milky Way, Sagittarius a star, this is particularly promising. Because it is much closer than M87, its environment changes on a timescale of minutes rather than days, meaning we could potentially witness significant fluctuations in a single observing session. This push toward dynamic observation is more than just a technical upgrade. It is a shift in how we probe the fundamental nature of gravity. By watching how the black hole's shadow evolves, we are no longer just testing the static predictions of general relativity. We are testing its predictions in a dynamic, real-world scenario. It's the difference between studying a still photograph of a waterfall and watching the water cascade over the rocks in real time. The motion reveals the underlying forces at work. Every flicker, every bright spot that moves around the shadow, is a data point that tells us about the stability of the orbit of photons, the frame-dragging effect of a spinning black hole, and the very nature of the spacetime continuum near its breaking point. The next generation of the Event Horizon Telescope promises to turn these enigmatic shadows from static icons into living laboratories, giving us a front-row seat to the cosmic dance where light itself is pushed to its absolute limit. We have journeyed through the firewalls and the fuzzballs, the singularities and the holograms, but our final mystery asks the most radical question of all. What if we have been fundamentally mistaken about the nature of these cosmic dark spots? What if black holes, as predicted by general relativity, do not actually exist? This is not a fringe idea but a serious, albeit highly speculative, attempt by theoretical physicists to resolve the deep paradoxes we've encountered. The proposal is that what we observe as black holes are, in fact, something else entirely: exotic objects like gravastars or dark energy stars, which mimic the key properties of a black hole while skillfully avoiding the mathematical and physical nightmares of a true singularity. The motivation for these ideas is born directly from the conflicts we've explored. The singularity is a clear sign that general relativity has broken down. The information paradox and the firewall dilemma create seemingly impossible choices between our two great theories of physics. What if the universe, in its elegance, has found a way to avoid these problems altogether? What if matter, on the verge of gravitational collapse, does something other than crushing itself into an infinite point? This is the premise behind the gravastar, a term blending gravitational vacuum star. Imagine a star so dense that its core is no longer made of atoms or even neutrons, but has undergone a phase transition into a new state of matter, a bubble of dark energy. Dark energy, the mysterious force causing the universal expansion to accelerate, is characterized by a powerful negative pressure. In a gravastar, this negative pressure could act as a perfect counterbalance to the immense gravitational crush. The structure of a hypothetical gravastar is fascinatingly layered. Instead of an event horizon, it would possess an ultra-thin, super-dense shell of matter, perhaps only a planck length thick. This shell would be what remains of the original star, frozen in a state of near collapse. Inside this shell, the interior would not be empty space leading to a singularity, but would be filled with a core of dark energy. This dark energy core would have a constant negative energy density, creating an outward pressure that exactly halts the gravitational collapse. From the outside, a gravastar would look almost identical to a black hole. Its gravity would be incredibly strong, bending light into a shadow-like feature. Matter accreting onto it would form a hot, bright disk, and it would possess a crucial defining characteristic: an innermost stable circular orbit for particles, just like a black hole. For all observational intents and purposes, it would be a black hole imposter, but with one crucial difference: there is no point of no return. There is no event horizon. An object could, in theory, fall onto the shell, but it could not pass through to an interior that has, in a sense, been walled off from our universe by this phase transition. The appeal of such a model is immense. It immediately erases the singularity, replacing the point of infinite density with a physically plausible, albeit exotic, dark energy core. This alone solves the breakdown of physics. It also offers a potential resolution to the information paradox. Since there is no event horizon to trap information forever, and no singularity to destroy it, the information about anything that collides with the gravastar's shell could, in principle, be preserved. It might be scrambled and released as thermal radiation in a process similar to Hawking radiation, but without the paradoxical loss. The firewall dilemma vanishes because there is no horizon to be smooth or fiery. The surface of a gravastar is a physical boundary, and interacting with it would be a violent but information-preserving event. However, for all its elegant problem-solving, the gravastar model faces severe and perhaps insurmountable challenges. The primary hurdle is stability. The proposed shell of a gravastar exists in a state of perfect, precarious balance between two titanic forces: the inward crush of gravity and the outward push of the dark energy core. Physicists have run detailed simulations, and this balance appears to be fantastically unstable. The slightest perturbation, a vibration, a particle impact, anything, would likely cause the shell to either collapse inward, presumably forming a true black hole after all, or to disintegrate outward. It's like trying to balance a pencil perfectly on its point. In theory, it's a possible state, but in the messy reality of the universe, it's effectively impossible to achieve or maintain. Furthermore, the nature of the phase transition required to create such an object is completely unknown. We have no theory that describes how normal matter would spontaneously transform into a shell of exotic matter surrounding a dark energy core under such extreme conditions. The question then becomes a profound one about the nature of scientific evidence. If a gravastar and a black hole are virtually indistinguishable to our current telescopes and gravitational wave detectors, how can we ever tell them apart? The most promising avenue lies in the precise study of the black hole shadow, particularly with the next-generation Event Horizon telescope we just discussed. A true black hole shadow is defined by its event horizon and the photon ring. A gravastar, having no event horizon but a physical surface, might cast a slightly different shadow. The light echoes and the behavior of matter at the very edge could have subtle signatures. For instance, if some material were to somehow be ejected from this boundary, it would be a clear sign that we are not dealing with a classical black hole. Gravitational wave astronomy also offers hope. The ring-down phase after a black hole merger, the final ping as the new object settles down, would have a different set of frequencies if the object were a gravastar with a physical surface rather than a perfect event horizon. Detecting these deviations is the holy grail for testing such alternative models. So, are black holes actually dark energy stars? The honest answer is that it is highly unlikely, but the value of asking the question is incalculable. These exotic models serve as crucial stress tests for general relativity. By imagining a universe without singularities, physicists are forced to identify the unique, testable predictions of Einstein's theory that cannot be easily mimicked. They push our observational techniques to their absolute limits, searching for the faintest deviation that could signal a revolution. The gravastar hypothesis, in all its speculative glory, reminds us that science progresses not only by confirming our ideas but by rigorously trying to break them. It embodies the spirit of exploration that has guided this entire journey, a willingness to venture into the unknown and consider every possibility, no matter how strange, in our relentless quest to understand the true nature of these darkest and most brilliant mysteries of the cosmos. And so our journey through the abyss comes to a close for now. We have ventured from the fiery paradoxes at the event horizon to the terrifying unknown of the singularity, from the cosmic scale jets powered by invisible magnetic fields to the potential that our entire universe is a holographic projection. These 30 mysteries are not merely a list of unanswered questions. They are a map of the frontiers of human knowledge, charting the very places where our understanding of reality fractures and fails. Black holes are far more than cosmic vacuum cleaners. They are the universe's ultimate laboratories, forcing our two most powerful theories: the grand, geometric rules of general relativity and the spooky, probabilistic laws of quantum mechanics, into a direct and violent confrontation. Each paradox, from the loss of information to the threat of a firewall, is a beacon illuminating the path to a deeper truth. This grand synthesis, this long-sought theory of quantum gravity, remains the holy grail of modern physics. It is the key we need to unlock the final secrets of the singularity, to understand the true nature of the Big Bang, and to answer whether information, causality, and time itself can survive the universe's most extreme environments. The quest is underway, driven by the brilliant minds exploring string theory, loop quantum gravity, and the holographic principle, and aided by revolutionary instruments like the Event Horizon Telescope and gravitational wave observatories that are turning these theoretical phantoms into observable phenomena. Every new image, every ripple in space-time, brings us closer to a revolution that will likely reshape our conception of reality as profoundly as the theories of Einstein and Bohr did a century ago. The true wonder of this exploration is that it reveals a cosmos that is far stranger, more interconnected, and more magnificent than we could have ever imagined. Black holes are not just destructive ends. They are potential gateways to new physics, to new universes, and to a fundamental understanding of space and time. They humble us, reminding us of how much we have yet to learn, while simultaneously inspiring us to push further. The darkness they hold is not empty, it is filled with the promise of discovery. Now, we turn the question over to you. Which of these 30 mysteries captured your imagination the most? Does the holographic principle bend your mind, or does the terrifying possibility of a firewall keep you up at night? Share your thoughts in the comments below. We'd love to continue this cosmic conversation with you. If you enjoyed this deep dive into the unknown, make sure to subscribe and hit the notification bell so you don't miss our next journey to the frontiers of space, time, and understanding. Thank you.